What you see on that slide is a list of energy systems that you need to office training in for 1 year, where we take a really deep dive. We're going to cover some of them in 1 day. So it's going to be a high level where there's much focus on learning and leaving some value, so that when you leave here today, you can go back and apply some of this in your plants. Steam systems, we're going to take a particularly high-level look at steam systems optimization. I'm going to share some tools with you. I'm going to show you how to determine boiler efficiencies, how to calculate steam leak losses, and show you a way to scope your steam system so that when you go back to your plant, you're able to determine your steam system operational efficiencies and benchmark that against other steam systems in Nigeria or other steam systems in your sector. In terms of optimizing electric motor systems, if we look at, and this is a European statistic done by Professor De Almeida from Coimbra University, if we look at electricity consumption in the European industrial sector, 73% of that is contributed by electric motors. So what that says to me is that if I can optimize my motors, I can make a big impact in my energy performance in my plant. If we decompose that somewhat and we look at the motor system's electricity consumption by application, what we find is that air compressors, pumps and fans account for more than 50% of total motor consumption in industrial plants. And those are the ones that we're going to touch on very likely today. Cooling or chillers and refrigeration compressors, conveyors account for significant slices as well. But it's particularly in the centrifugal devices like fans, pumps and compressors where you can expect really great savings. And I will demonstrate that through a few worked examples and explain to you why that is the case and why it is that when we do systems optimization, we focus on the relationship between energy consumed and centrifugal devices. And we exploit the benefits of the cube law in that regard, power cube law. So the approach we take is essentially a systems approach. And this is a case study of a electric motor in a pump system application. So what we have here is we have the components. First of all, we have a lead. And the requirement of the process is 31 units of fluid power. But in delivering that 31 units of fluid power, we have a motor with a standard efficiency. It's a standard efficiency motor of 90%. We've got a coupling with an efficiency of 98%. We've got a pump that is 70% efficient, according to their nameplate data. And what we find, because the motor and the pump is oversized, we need a throttle. We need to throttle that. The throttle, 60% throttle. And then we've got a pipe efficiency of 69% to achieve our 31 units of fluid power. What we then see is, because of that, a lot of that fluid power generated, or the pressure generated by the motor and the pump, is throttled by 60%. You know, we could argue that our motor is 90% efficient. That's pretty good. The question is, to achieve that 31 units of output power, and to accommodate the losses that I've circled, we need input power of 100 units. Effectively, what that means is that our system may not be as efficient as we think it is. So my question to you in this motor and pump system case study is, how efficient is that system? How efficient is that pump system?
Very good. Thanks a lot.
Yeah, you guys are getting into it. Add something? Okay, let's move on. And before I look at that closer and respond to the answers I got, let's talk about the motor, and let's talk about motor efficiency. Motor efficiency is really a ratio of output to input. So motor efficiency is about shaft power divided by the electrical power absorbed by the motor, supplied to the motor. And shaft power is essentially this formula on the right hand side. We're going to talk a lot about these two here. T is torque. Torque is a force along an axis, and it's proportional to power. And then we got this omega in lowercase. And omega is the angular speed, or the rotational speed in radians per second. In terms of defining system efficiency is the product of all the component efficiencies in that system. So system efficiency for a pump, a motor, a fan is the product of all the component efficiencies in that system. So let me ask you this, that if you had a system where you got three components, that there is your system, and the efficiency of each of these components is 90%. What is your system efficiency? Is it equal to 90%? Is it more than 90%? Is it less than 90%? 90%? Sorry. Less than 90%. Anybody disagree with that, gentlemen? Less than 90%. You say 90%. Okay, so we've got some interesting views. Let us see what it is. I want you to take your calculators, and I want you to do the following. 0.9 times 0.9 times 0.9. What do you get?
0.7.
Sorry?
0.7.
72.9%. That is the system efficiency. And I want you to understand this, that your system efficiency will always be lower than the lowest efficient component in your system, your energy system. And we will now apply that thinking to what we have in our case study. So, system efficiency in our case study that we have is the product of the efficiency of the variable speed or frequency drive, the motor, the transmission or the coupling, the end use. And we will see that applying that now, we have that efficiency of 31%. Multiplying 90% by 98%, by 77%, by 66%, by 69%. So the question is 31% acceptable? You know, we had a motor with a 90% efficiency, but the system efficiency is 31%. So don't get fooled by great efficiencies within the components of your system. It's about the motor system, and that matters. It's about the overall system efficiency that matters. And quite honestly, the response was from this table, not acceptable. 31% is a very poor system efficiency, and we need to address that. So now we address that. So where we had an oversized motor and pump, and we had to throttle it, we removed the throttle. What did we install? We installed a VSD with an efficiency of 95%. We replaced that with a high efficiency motor with an efficiency of 95%. It then a coupling efficiency of 99% and a more efficient pump at 90%. We noticed we removed the throttle that was over there. We now have low friction piping with the efficiency of 90%. So we're still delivering the 31 units to the system. That's what the system needs. But considering the efficiencies of that system, we now only need 43 units of input power to achieve 31 units of power required, or fluid power required by the process. So by optimizing those individual components, we were able to reduce that significantly, and we now have a system efficiency of 72%. And in a way, you could say we created a virtual power station with 57 units, because think about it this way, if you haven't done so already. Every kilowatt hour you save, you remove a need from the Nigerian electricity grid to generate a kilowatt hour. So when we say kilowatt hours, when we say energy, we see it as the creation of a virtual power station in Nigeria. And that is the essence of it. Government doesn't have to expend a lot of capital, a lot of resources, a lot of time in investing in a new power station, because energy efficiency is always considered the first fuel. And if I listen to the feedback you gave on day one, then it is clear to me that a lot of you were interested in improving your energy efficiency and improving the energy management system in your plants. And we're going to spend the day looking at some ways you could do that and contribute towards that. Right, so the systems optimization approach has been shared, and that's critical. And our experience has shown that when you undertake a systems approach, you can unlock savings of between 5 and 40%. And I've seen that. So that's not an American or European telling me that. I've seen it happen in South Africa, I've seen it happen in Morocco, Sri Lanka, I've seen it happen on our continent. As opposed to calling your motor salesman in and just looking at your motor, where savings normally vary between 1 and 4%. So if you're upgrading your motor from an IE0 or IE1 to an IE3, maybe that's what you can achieve, 4%. But if you were to look at the full system, you're highly likely to unlock a great deal more savings. So where do we start? We start looking at reviewing the load requirement first. That's number one. That's where we start. So we don't run to the pump house. We don't go to the boiler. We don't go to the boiler room. We don't go to the compressor room. We go to the process. And we see and we observe and we interrogate how energy is used. Do we need it to do that way? Can we do it differently? Can we batch it and instead of having the motor run all day or the curing tunnel run all day, can we reduce the time by making sure we don't run it unloaded or very lowly loaded throughout the day? Once we've done that, we then look at reviewing the complete system and identifying low-cost opportunities. Now what we have learned from that is when you look at systems optimization and you decide to effect a change to a particular component in that system, you need to understand and be aware of how the change in that component affects the performance of the other components and the system as a whole. So you can see we're not doing it the conventional way. Conventionally, when I had a problem with my compressed air system, the vendor would come on site and guess where we would go to? Straight to the compressor. We're doing things differently now. So we're saying, how are you using compressed air? Why are you using it that way? Do you need to do it at that pressure? Why do you see such a big pressure drop from your drops to your equipment compared to what's being generated in your compressor room? That's the way and that's the direction in which we now work. And once we've done all of that, finally, we review the motor and the motor drive system. So that is where we end. But it's not the other way around. That is critical. So that's a motor system. That represents a motor system. What we did here is we drew the envelope around that. So besides the three-phase input power from the utility or from your own generator, you have within that the elements that comprise the motor system, that if you need to achieve the systems optimization, we want to be able to look at the impact of each of those components, not in isolation, but within the context of the whole system. So what we have is a motor drive subsystem over here, which is the drive and the motor, and we have a mechanical subsystem here, which is the coupling and the load. The load can be a pump, a fan, a compressor, anything like that. And ultimately, this is where we start. This is the process. This is where we use the fluid power. This is where we use the fan power. This is where we use the steam, the compressed air. So we will start there. And based on the demand and how that demand fluctuates, it will indicate and feedback to the pump or the fan, it will feedback to the coupling, and it will feedback to the controls, and determine what changes need to occur to meet a changing need or changing process requirements. So that is how we see the electric system, and our experience has shown that doing it this way will unlock a great deal more savings. Some of the motor technologies we're going to talk about. We're going to talk about one of the workhorses of the industry by doing this. Electric motors, we have essentially split up very broadly between DC motors and AC motors. DC motors are largely old technology, although we're starting to see DC motors, especially as in electrically commutated permanent magnet, brushless motors, and permanent magnet motors still being utilized, as we see innovations in that regard in industry. The focus, though, in industry is on AC motors. That's where we're seeing some of the biggest growth. And in terms of our course today and the work today, we're going to focus on the workhorse, which is the induction motor, the squirrel cage induction motor. I've prepared a video. Before I move on, I'm going to try and play it. I don't have an audio connection, but I'll try and play it and see if it's audible to everybody in the room.
Would you mind if I read?
The squirrel cage induction motor. Squirrel cage induction motor is used in more than 90% of electrical motor systems globally. In fact, in the work I did in Ghana, we found that low-loaded squirrel cage induction motors was the singular biggest contributor to low power factor in that country. It's a workhorse of industry. It's the motor style and type of design that we use most frequently. In the squirrel cage induction motor, we have over here the actual squirrel cage around the stator. We have the rotor. We have some of the rotor laminations and the three-way electromagnetic windings in the rotor. And we have a cutaway of the motor itself. The induction motor provides really good reliability and good efficiencies. It's reasonably cheaper than most of the other motor brands. And the good thing about the squirrel cage induction motor is that it lends itself very well to application with variable frequency or variable speed drives. Just as a exploded view of the squirrel cage motor, the important bits, as I said, number one is the front and the back bearings. We'll talk a lot about those bearings. They're one of the biggest causes of failures of motors at a time. A very simple thing like using the wrong or not enough, too much lubrication. Then we have the rotor, and we have the stator. And this is where we have the fan, because cooling is such a big issue within electric motors because of the high I squared R or Joule losses we have in motors. What rating should that motor be? And what mounting is? And the good thing about the squirrel cage induction motor is that it lends itself very well to application with variable frequency or variable speed drives. Just as a exploded view of the squirrel cage motor, the important bits, as I said to you, number one is the front and the back bearings. We'll talk a lot about those bearings. They're one of the biggest causes of failures of motors at a time. A very simple thing like using the wrong or not enough or too much lubrication. Then we have the rotor, and we have the stator. This is where we have the fan, because cooling is such a big issue within the electric motors because of the high I squared R or Joule losses we have in motors. So let's talk about those losses. One of the biggest losses we have in induction motors is what we call the electrical losses, also called the Joule losses, as expressed by I squared R. And those are the losses that result in excessive heat, especially as we increase the loading on the motor. So the heat generated by that is essentially the loss. And the heat both generated by the stator and the rotor that gives rise to very large Joule losses. Magnetic losses occur because of the steel laminations in both the stator and the rotor. And then we have mechanical losses, a bit smaller than those. They are essentially the bearings, failure of bearings, ventilation, bad or inefficient or insufficient ventilation, and wind leak losses. Stray rod losses are also relatively smaller due to leakage flux, harmonics in the air gap flux density. That's where we have those losses. And then there's the brush contact losses, where you have a brush motor where you have a loss, a voltage drop between the brushes and the commutator. Those are losses. So let's be aware of the biggest loss. The single biggest loss on this slide, or the single biggest loss in your induction motor will be your electrical losses.
Your mechanical losses are much smaller, and we will have a look at the extent of that. But that is where you will encounter major problems because of that heat that's expressed as a joule of electrical loss. We have challenges to keep the motor cool. We have challenges to manage the motor temperatures through insulation and other ways. We also have of late started to see a lot more of that, harmonics, and the destructive effect of harmonics on electric motors, especially when you're using a variable frequency drive. The harmonics generated by VFDs are essentially the third, the fifth, and the seventh harmonic. The fifth harmonic is one of the most destructive. I've seen motors burn out. I've seen motors virtually go up in flames in automotive plants in South Africa because of harmonics. So how do you manage harmonics? How do you manage power quality? Through filters, back-end filters, we'll talk about that a bit later. If you want to quantify that, maybe prioritize that, I mean, this diagram shows you the extent of the I squared R losses, the electrical losses. That is that much there. And it decreases as we see the motor size increase, but significant in terms of any motor under 75 kW. That's the windage losses. Those are the losses due to the mechanical losses due to bearing failure and the like. And as we've seen more and more, some of the stray load losses occur because of harmonics. That is starting to grow and become a bigger problem, especially in the larger motors. This is a motor loss chart for a 50 Hz 4-pole induction motor. Motor standards. Now, many motor standards have been developed, and I think we need to be aware of the two standard organizations. We have the American Motor Standard Organization called NEMA, which is the National Electricity Manufacturers Association of America, and they developed this standard. And at one stage, the standards were quite different to what we were using outside America. Then we have IEC, the International Electrotechnical Commission. They are a standards body. They develop standards for motors. And in terms of the standards for motors, 15 to 20 core motor standards are from IEC 6034 and 672 that define the motor classification. And with the development of IEC standards in motors, we're starting to see parity between what the Americans use and what the rest of the world use today. So I'm going to share with you one of the standards, the standard that speaks specifically to motor efficiency classes, and what that means in terms of motor efficiency as you go up one step or you go to a different class. IEC 6034/30/1. There are many more than that. As I said, 15 to 20 core standards in that, and IEC 672. Now, this particular one, 634/30/1, defines the efficiency classes for single-speed motors for operation on sinusoidal voltage supplies. In other words, direct in line. It harmonizes the different efficiency levels in use around the world, especially between America and the rest of the world. And it establishes a limited efficiency value based on the frequencies, whether we are at 50 Hz as we are in Nigeria and in the rest of the world, or 60 Hz as we see in America. For a range of poles, number of poles from 2 to 8, and motor power ranging from 120 watts to 1000 kilowatts, 1 megawatt. No distinction is made between motor technologies. So whether it's a synchronous motor, permanent switch magnet, an induction motor, it applies to all of them. And what does it look like? These are the 4 efficiency classes from IE1 to IE4. And in the old designation, we used to use motor classifications of efficiency 1 and efficiency 2. Those are largely being replaced. I still go into a lot of old plants and find some of those old motors. But it's now IE1, IE2, IE3, and IE4. And as I work with industry, I'm starting to see that IE2 really starts to lose its value. Because the performance or the efficiency increase from IE1 to IE2 is quite small. And many companies are now opting to make the jump from IE0 or IE1 and go straight up to IE3 because it's a significant improvement in performance and an improvement in motor efficiency as well. IE3 has 16 to 20% lower losses than IE2. So that's becoming the favorite now. IE4 is super premium efficiency. I've seen some of them, I've seen more and more of them. My work in Sri Lanka is showing that IE4 is now being applied. And we are not saying to companies, go out and replace your motor to an IE4. What we are saying and have a policy that when your motor fails, you make the decision of whether you're going to rewind or replace. And we'll talk about that. But when you replace it, it's a wonderful, it's a great, perfect opportunity to consider upgrading the efficiency class of your motor to an IE3 or an IE4. Then we have, in addition to that, we have the IE5. It's included in the index purely for information purposes. It has the goal, listen to this, it has the goal to reduce the losses of the IE5 by 20% relative to the IE4. So it's still experimental, it's not commercially available. It's been used in some application in space travel. So Professor de Almeida at the Coimbra University in Portugal is one of the leaders in the work of motor development, and it's through the work of Anibal in Portugal that saw the European migration from IE0 to IE3 and IE4 today. Most European industries are now using IE3 and IE4 because of what they did, what he did. And to me, that's a no-brainer. And it was a no-brainer for me in South Africa because we don't have motor manufacturers in South Africa. So when I spoke to government and said to them, why don't we set minimum standards for motor class efficiencies in South Africa? They wouldn't do it. It was not as if we were going to affect or impact on a South African motor manufacturer. So we have missed that opportunity. And in the same way, I say to you in Nigeria, this is a wonderful opportunity to elevate the efficiency of industry, to elevate the efficiency of electric motors in your country, is by considering minimum standards. Why do you think in China, the Chinese government sets minimum standards for foreign companies, but not for their own companies? So the move to move away from standard or IE1 efficiency motors has huge benefits, and we'll talk about some of them. There's a caveat, there may be some, I think, some cautionary caveats we have, but motor efficiency is quite a straightforward opportunity to exploit when you have a motor that fails.
Okay, I was just wondering if you can shed more light on what are the structural changes or modifications manufacturers make in these motors to improve their efficiency. Is it bigger winding, more efficient bearing, or?
Yeah, no, that's an expert question. That's a question for the expert train, but a very good one. So what we see is they seek to reduce the electrical losses, the big electrical losses. So they're looking at windings. In some cases, they dispense with that three-way electromagnetic windings, and they replace that with rotors with no windings at all. They reduce the flux density losses. They look at the materials used in motors. We are finding now that some of the high efficiency motors are using rare earth metals. If you have a new Ingersoll Rand or Atlas Copco compressor, I can bet that the motor in that compressor would be one where they're using some of the rare earth metals, where there's not a lot of heat dissipation. So you don't heat up the windings. The heat from the windings is from the electrical resistance to the current flowing through it. And that is what they are focusing on. So IE4 and maybe IE5 and beyond that all seek to reduce the losses we spoke about and to be more effective in the way we deliver the sharp power that we need. That answer the question? So if we look at the efficiency classes of IEC 6034/30/1, then we see this graph is output power, and this is motor efficiency. We can see here till about that point that the differences between the IEE 1, 2, 3, and 4 are very small. It is really when we look at the direction beyond this that we start to see significant greater improvements in energy efficiency when you upgrade from one motor class to the other. So each of those graphs, that would be IE1, IE2, IE3, and IE4, and the dotted one would be the IE5. And the way the IEC standard classifies motor efficiency, as you would see from your nameplate, that would be the nominal operating point for a IE class motor. And we define that for different loads, for 75% and for 50% load. So consider the opportunity that present themselves to you when you have a need to change the motor. So often in plants, because we don't maintain our motors well, when the motor fails, it's a surprise. And because we have not taken the measures to back up that with inventory, we look around and we grab the nearest motor just to keep the plant running. And we say to ourselves, I'm going to get it in, on Monday we'll find the motor and we'll replace it. You know, Monday never comes. A year later you're still using that motor. We're going to talk about some of the things you need to consider when you select the motor. We've spoken about the energy efficiency class of the motor and the importance of that. We're going to talk about many of the other factors that influence making the best decision when getting a motor or replacing an existing motor. So this is a work example, and I want to go through this with you. So here we have the option of a 75 kW motor. That's the existing one. That's kW. Or replacing it with an IE1 or an IE3. That's an IE0. That's a standard efficiency motor right there. So when we analyze that, and this is the kind of work you need to do to justify this, don't go to management and simply say, I want it because Al said so. No, you need to do that. You need to provide some proof of concept. So we look at the efficiencies of the different motor types. We look at the motor cost, and you can see that IE3 is significantly more expensive than the IE1. We look at the operating hours. This motor runs fairly constant. It's like a one service level motor, 8,400 hours a year. The load factor will be the same for all motors. We calculate the output energy and the losses and the energy costs. The bottom line is that payback on the IE3 motor is 6.6 years compared to 10 years for the IE1. So it starts to become a no-brainer. This is in US dollars. But whatever you buy your motors in, the proportionate differences should be quite similar. So, as I said earlier, I am finding that very often when an IE0 motor fails, and in rewound 3 or 4 times, they don't want to rewound it again, they will go straight to IE3. The benefit there will be significantly higher, or noticeable, compared to taking a small step up to your IE1 or IE2. So, Michael, you can let me know when it's tea time. I didn't get a program today. Can we get a program? Yes. You need it? Please. Oh, man. We're going to keep on running until I hear from you guys. So, motor selection becomes quite a vexing thing. You know, you can't assume that the people who designed your plant originally did a good job. You need to interrogate the load, the circumstances, the requirements, the electrical system, a whole lot of things to decide which motor would best suit your application. Many times I go into plants and I would find that the motors that they have in operation are oversized. And when I question why they are oversized, it is because we were expecting an increase in production capacity. But that expectation was never realized. And 5 years later, I am still operating the motor at 40% load, incurring big power, low power factor, and very low efficiencies. And we've done a study of that in the program, where we've taken an operation and we said, let us assume there's a likelihood of you increasing your production output and your motor power demand in a year or two's time. Let's assume that. Size your motor now for what you need now. And in 2 years' time, if that happens, you upgrade, you increase your motor size. And in all the examples we've done, we have found that we variably save energy by doing that. Instead of getting a big motor in now and running it at a very low load until we have that upgrade that we thought we'd have. But just be aware that I see a lot of that. I also see a lot of redundancies when I go into plant. For non-critical processes. Now, when I'm at a petrochemical plant and they have 300, 400% redundancy, I can understand that for critical processes, but you cannot afford to stop the operation. But you don't need redundancies in every single motor application in your plant, so be very circumspect about deciding whether it's necessary for that redundancy. I can always see where there's been a very good motor salesman, in that people have motors too large and too many VFDs for what they need. The salesman was very good, the salesman made them buy it unnecessarily. So I'm very wary of those salespeople too. I'm not saying they're bad, I'm just saying they're doing what they are very good at. You need to do what you're good at, and make sure that you get to your plant what your plant needs. So some of the factors that you would consider in selecting an appropriate motor for your plant. There would be the mechanical requirements of the driven load. What are the mechanical requirements of the driven load? Is it something you're going to, is it a pump? Is it a fan? Is it a hoist? Is it a conveyor belt? You will need to decide the motor efficiency classification you're going for. Do you need an IE4? Is it really necessary? You need an IE2 at all. You need to consider the electrical distribution system. How far am I away from my EVs? How far along the cables run? You incur significant losses over the length of cables. You will look at the physical and environmental consideration. Do I have enough space for the motor? Can I mount it there? Or to be mounted horizontally or vertically? If I'm going to install a VFD, is there a clean environment? Is there a dust-free environment to ensure that my VFD doesn't fail? Is there space to install my harmonic filter? So evaluate all of these to ultimately decide, do I need a AC or DC motor? Do I need a single or three-phase motor? What size in terms of power rating should that motor be? And what mounting arrangements do I need, etc., etc. So those are the considerations. You don't simply say, what have we got? We've got a 30 kW induction motor, what's that nameplate data? Let's get another one the same size. In industry, life doesn't stand still. In industry is very dynamic. Things change. They put a new production line, they close the production line, they expand the plant, they change the product mix, they change the working hours, they change the working conditions. So don't assume what you see in the plant as it fails as being the correct or most appropriate motor for your requirements. Interrogate that. Right, so this is a motor for a induction motor. This is a nameplate for induction motor. I would like to challenge you to tell me what you want. What is that nameplate telling you? What?
Telling you information about
What information?
to tell you if it's connected inside the tap.
Show me where it says.
If you let me know if I'm connected inside the tap or not inside the tap, direct online, not inside the tap.
Sorry.
Like direct online or not direct online, to let you know. And from here now,
How do you see that?
zero
Yeah.
is direct online.
Yeah.
GEON. And this is this tap connection. it will let you know, it tell you the RPM, the speed we can maintain, this is the RPM, the speed, this is the mass speed here. Then as you know the kilowatts, the power factor, and so on. This is the kilowatt, this is the hours, and this is for the let you know the type of voltage you can apply across the motor. This is 380. We can take up to 380 in a data. You can use 380, start with 660 Y. For you can use up to 450 volts, 460.
They are.
You can use up to 460 volts.
Have you got 60 hertz in Ghana? Do you use 60 hertz motors? 60 hertz frequency in Ghana?
Yes.
Okay.
Yeah, power factor.
Anything else you see?
Consider. And the efficiencies are being mentioned.
For different levels.
Yes. This is I that you are talking about, I theory. This is 96 to 95 and 8.
Okay. Thank you very much.
Okay, let me take you through this nameplates. Not all nameplates are as good as this one. It's still not complete, but let me share with you some of the value, some of the information I gleaned from nameplates. So it starts by telling me, so I look at the WEG motor, they're pretty good motors, they're manufactured in Brazil and South America. It's a IE3, I can pick that up immediately. I noticed there that it's a three-phase motor, so that's an indication of a three-phase motor. That's the frame size, that's the WGE code for frame size. It's a 4-pole motor. So if your synchronous speed in Nigeria is 3,000 RPM, 4 poles is 2-pole pairs. So it would be 3,000 divided by 2. So your synchronous speed would be 1,500 RPM. So I can see, I can determine that already. Then you've got IP55. IP55 are the conditions in which you can, the motor is specified to operate. IP stands for ingress protection. And IP55 tells me that I can operate this motor in dusty conditions and low pressure water jets. I can operate this motor, I'll be okay. You have an IP88. An IP88 is a classification for a motor that you can operate for long durations fully submerged in water. So that classification tells me where and how, under what conditions I can operate my motor. Then I've got insulation class F. We're going to talk about these things in a minute. But that tells me that the insulation of the windings and the insulation of my motor limits me to operating temperatures of 155 degrees Celsius. Years gone by, we used insulation classes that were lower than that, and whenever we overheated the motor, it burnt. It's a small price to pay for peace of mind. So that's become very common today. High insulation class F. Then we have a delta T of 80 degrees Celsius. That delta T of 80 degrees Celsius is the temperature difference between ambient temperature and the hottest point of your stator winding. So I would take a temperature gun. I can't see the stator winding inside my motor. I will show it on the casing and I will take that temperature. I will take my ambient temperature reading, and the delta T should not exceed 80 degrees. If it exceeds 80 degrees, I'm starting to compromise my thermal insulation and my thermal inertia of my motor, and I'm starting to approach dangerous levels of operation. So when I talk about that K, it varies from manufacturer to manufacturer. It could be a measure of the inrush current, or it could refer to the frame size as well. That's your duty factor. Duty factor 1. An IEC has 10 duty factors. So the duty factor of S1 means you can operate that motor constantly as you build up to thermal equilibrium. We have other ratings for intermittent use and things like that. Then we've got the service factor, and the service factor indicates whether you can operate that motor above its rating of 185 kW. And in this case, no, you can't. If you operate this motor above 185 kW, you will shorten the motor life and you may even cause it to fail.
Then we have ambient temperature. Ambient temperature is not the temperature in Ghana, it's not the temperature in Lagos, not the temperature down this road, it's the temperature where the motor is. That's your ambient temperature. And you should not be operating, in this case, with this nameplate, you should not be operating this motor in an environment with a higher ambient temperature than 48 degrees. Otherwise, you derate your motor. I will show you now how you derate your motor. When I have these voltage classes, I have star delta. It tells me that I can operate this motor from either 380 or 400 volts, which is my delta, or my star voltage of 660 to 690 volts. I can configure the wiring to enable me to do that. It tells me this is a 50 hertz. This motor can be used in a 50 hertz frequency, power frequency environment, and the 60 hertz environment. So you can operate this motor in Europe, Nigeria, and America. It gives you the RPMs, and you can see if the synchronous speed is 1,500, you can see the degree of slip that I'm having at different levels of voltage and current. Significant slip. I'm talking 50 hertz. This year, 60 hertz, that would be another measurement for slip with different parameters. You'll see voltage, you see speed increases as the voltage increase. We here are full of amps, so dependent on whether you wire it up in a delta star arrangement or not. The power factor you get for each of those IE3, and what the efficiencies are for different load factors. What we are finding is that a lot of small induction motors are specified for loads 50, 75, and 100. Particularly at 75%. So small induction motors are specified for maximum performance at 75% loading. So when you specify your motor size, or you determine your motor size for a small induction motor, do it on the 75% load setting. What else? This year tells me what the lubrication I would need, the quality of the lubrication I would need at the bearing, the front and back end of the motor. It tells me how many grams of lubrication I must use at what intervals, at 1100 hour intervals. It gives me the quality of the lubrication, mobile polyrex gear. So it tells me the lubrication. Don't have to be a rocket scientist, just do what the nameplate says. Don't put too much, don't put double the amount, don't put too little. Those are specified by the manufacturer. This motor, more than 1,000 meters above sea level. I looked up, Lagos is about 30 meters, 1 to 30 meters above sea level. Abuja is about 850 meters above sea level, so you're okay. In Johannesburg, because of the altitude, we have to derate our motors by 5%. In a plant in Mexico where we did some work, we had to derate the motors because of the high ambient temperature in the plant. We had a particular operation in Johannesburg that had to derate the motors by 20% because of altitude and because of heat. So those become very important factors. If you think you've got a 185 kW motor, you could have a 150 kW motor because of the derate, and we'll share some examples of that. So that's the nameplate. The other thing that nameplates also tell you, it will tell you if the motor turns clockwise or counterclockwise. Some motors can do them both. Some motors are wired to do them both. Like when you have conveyor belts, stop and move back, you will have the motor being able to turn in those directions. So knowing those are quite important. But in the design of the motor fan, they've accommodated the fan impellers so that they're not angled. You look at a motor impeller, the fan is straight because it's to accommodate cooling spinning in both directions. So motor nameplates are important in defining just what the motor can do and whether it suits your application or not. Motor load. Here I have a story of motor load. Because experience has shown that most motors are oversized by 35%. Let me explain to you how that happens. So the plant decides they need a motor or fan to cool a process down, or you need a pump to provide water. So the production manager will say to the plant engineer, I need air. I need 600 kilograms per minute of air at 25 degrees for my process. So he bumped it up a little bit. The plant engineer says, you know what? He always gives me conservative numbers, and when I don't achieve it, he comes to squeal at me. So I'm going to bump that up. Instead, I've calculated I need a 30 kW motor, I'm going to make it a 35 or 40 kW motor. The plant engineer phones procurement and says, please get me a 40 kW motor, induction motor in the States. Procurement says, I know him, he's always under specifying these motors, so I'm going to add another 5 kW motor, just to make sure that he never runs out of motor power. So the procurement now buys, puts out a course for it, quotation for 45 kW motors. So the salesman sees this RFQ, the salesman says, you know, that company always under-specifies the motor sizes. I know that, I'm going to give them a 50 kW motor, just so that they're always happy, they're never going to be short of motor power. So what started as a 30 kW motor, now is now being a 50 kW motor. This is not uncommon, I see this in plants. I see oversized motors in plants. Oversized motors affects a lot of things. You must now ensure that all the other electrical equipment around the motor is sized to that level. Because you allow your motor oversized, you'll be running it at lower loads. Lower loads means low efficiency. Lower loads also means high, low power factor. So those are the challenges to do with oversized motors. I understand the need to have a rightly sized motor, but you need to be mindful of what it can cause. One good bit of tip from a really practical experience is, if you decide to replace a motor in your plant, start monitoring the power input to the motor over 2 weeks, maximum amount. You don't have to do it that long. But over 2 weeks, and there's a very inexpensive battery powered data logger that you can put onto your motor to log that information. And start to get a profile of the power input to the motor. It gives you a great insight into really what the true size of that motor should be. I spoke about operating temperatures, and the operating temperature on that nameplate we had was 100. So, you know, you pay a bit more, but as I said, it's good peace of mind when you know that your motor is insulated to withstand maximum temperatures of 155 degrees Celsius. Service factor. Service factor is an indication of the ability to exceed the mechanical power outputs over a sustained period. We saw that NEMA classification earlier where the service factor was 1.15, which meant that we could operate the motor 50% above the rated motor power. Thanks. So if we look at a 10 horsepower motor operating under rated conditions of a 1.15 service factor, it says to us we should be able to deliver 11.5 horsepower, which exceeds the NEMA allowable temperature rise for an insulation system. It may exceed the IP55. So if you operate that motor continuously at 115, at 11.5 horsepower, you will result in a reduced life of the motor, and the motor efficiency is reduced during operation of the service factor. So be aware of the service factor, and be aware of operating your motors above that. I did a pumps assessment at a large steel plant in South Africa. And what they did is they turned the impellers on one of the pumps. They had 6 280 kV kilowatt hour pumps, kilowatt pumps in parallel. And they were operating the one that they used impeller way above its specified rating. So they were heading straight for destruction of that motor. Motor efficiency is usually reduced in operation of the service factor. So be careful. Some people will see that service factor as an opportunity not to buy the next size motor. So they'll say to themselves, if I buy this motor and operate it at 10% above its rated rated power, I don't have to buy the next size motor up and I can save some money. It may be short-term anything that way because your motor is not going to last very long. So these are the de-rating factors. I want to just explain this to you. So according to that nameplate, this one is temperature and this one is altitude. So what happens is the ambient temperature of that motor was 40 degrees. So that is that area over there. When you start operating that motor at higher temperatures like 50, 60, 70, look what happens to the factor. Your factor falls significantly. So if I'm operating that motor at say 50 degrees, then I have to derate my motor by 0.88 or 87. Alternatively, if my motor, as per the nameplate, said that meters above sea level was 1,000, and let us say I go to a higher altitude, or a country with a higher altitude, or a higher point in Nigeria, and I'm now operating my motor on a mountain or a very high plateau at 2,000 meters above sea level. I need to derate that motor at 0.15. And how we do it, we use this calculation that says the new rating, the derated power of that motor is equal to the nominal power multiplied by the factor for temperature and the factor for altitude. So now what I'd like you to do, very quickly, just going to demonstrate this. I want you to calculate the derating factor, which you have is a 30 kW motor. And you're operating it at 50 degrees Celsius. And you're operating at an altitude of 1,500 meters. Using these graphs, tell me how much that 50 kW motor has been derated by. Anybody have the answer? Please show your hand. Okay, let me do the sum with you. So we're gonna calculate the power of the derated motor, which is the new motor. It's going to equal the nominal power, which is 30 kW, and we're going to multiply that by the factor for temperature. So if I look at the factor for temperature at 50 degrees, and you could be slightly different to me, but if I go to 50 degrees, this is the line over here, that's where I'm looking. 50 degrees Celsius is about 0.88. So I multiply that by 0.88, and the altitude is 1,500 meters, and I look at what I have on my derating chart, 1,500 meters. I would start going up at that point, and then across, so I'm about 0.97. I'm going to use the 0.97. times 0.88 times 0.97. Those are the calculators. What is it? Sorry? 25. 30 times 0.88 times 0.97. 25. Okay, so let's say it's 25. So what we thought we had was a 30 kW motor. What we actually have, because we're operating at 50 degrees Celsius and at an altitude of 1,500, is a 25 kW. It's a much smaller motor, significantly smaller. So if you're not getting the power, the shaft power you expect, because you derated it, because of the operating conditions, exceeding that specified in the nameplate. So your motor will perform and deliver the specified power if it operates within the limits of the temperature and the altitude defined in your nameplate. If not, you can have derating like that.
So what will be the effect of the new rating on the...
What will be the effects of the new rating on the power consumption of that motor?
You are still consuming the same amount of power. Sorry?
So try to explain to us, because I'm looking at it that when you derate, still having the same energy flowing into the motor. However, because of the altitude and the temperature, it's still taking that same energy, but it's being directed. So what will be the impact of the new rating on the energy consumption?
The new rating may not impact your energy consumption at all. Your motor, purely because of additional losses, is just delivering less shaft power. So to remedy that, you need either to change your operating conditions or you need to buy a bigger motor that when derated will give you 30 kW. And then you'll be consuming more energy. You are using the power absorbed by the motor. You're using the energy consumed by the motor, and you're delivering less because of greater losses. The flux densities, your electrical losses will be greater, your more heat losses. You may start seeing that your IP55 is no longer good enough, you need to go one up. You're going to pay more for that size motor because the insulation now is not good enough at hotter, at higher temperature levels. So while you're drawing the same amount of current to run the motor at maximum load, you're delivering less shaft power.
So he's not on this very topic, so he's still on electric motor. How do we measure the accuracy of an electric motor? Yes, how do we measure it? It's something we can do externally.
The IP classification given
Maybe we have the second question so that I can have some. Now, what was the supposed standard processing of running an electric motor?
talk about electric motors in a minute, but to just give you a quick answer, depends upon the vendor that does the rewiring. You need to make sure you get a good rewirer. A good rewirer can return your motor to you at the same level of efficiency it was prior to rewiring. When you pack the IP rating at all, the other temperatures for heating up electromagnetic coils is about 380 to 400 degrees Celsius. But you need to gradually take it up. You want to take it up fast because then you destroy the winding, then you destroy some of the insulation around those windings, the copper windings. So generally let me say poor rewinders will return the motor to you at a efficiency level of 1 to 2% less than what it was according to the ICA. The other question was about? I go by what the motor nameplate says. And the one way the motor nameplate gives me assurance is that I can operate my motor to 155 degrees Celsius without having to derate it, without having it to challenge the quality of the installation. I would use my temperature gun and check the temperature of my motor, check my efficiency, calculate efficiency the way I show you, and determine whether the temperatures I'm running at, it's below my micro rating, and I'm achieving the efficiency that I expect to get. Good question, thank you very much. Okay, so we talked about sizing motors. Tea time? How are you looking for tea?
More than 1 hour.
So now 1 hour to go for tea time.
11:40. 11:40.
Any other questions? Okay, we can move on to operating controls, because in selecting a motor, you need to be aware of the different operating controls at your disposal. How are you going to drive your motor? What are the different technologies available to you? What are the advantages? What are the relative costs? And whether the kind of process control you need, any one of these controls will suit your operation better. Before we get into that, let's just talk about the torque. So, operating characteristics of electric motors are defined in terms of their speed. Torque defined the mechanical rating of a motor. And the formula for torque in Newton meters is power in watts divided by speed. Speed is angular or rotational speed in radians per second. Newton, for those engineers refreshing or being a little rusty, a Newton meter is the amount of force required to move 1 kilogram of acceleration 1 meter per second squared. That is the definition of that. So expanding that, taking it to that level, torque in Newton meters is power in watts divided by 2 pi RPS. If you take a rotational speed, 1,490, 1,750, and multiply that by 2 pi, which is 6.28, and that will give you that. You need to divide it by 60, because RPM is in minutes, and you want to convert that to seconds. So torque ultimately is power in watts divided by 2 pi speed, RPM, divided by 60. And that will give you the torque. We can calculate the torque. We've got voltage, we've got current readings of the motor, we've got power factor, but you can also measure torque. Does anybody know how you measure the torque of a motor? Has anybody measured the torque of the electric motors? The instrument we use is called a dynamometer, where we measure the torque. There are other ways you could do it as well, less expensive ways to do it. But you can calculate torque. The torque is proportional to power. Synchronous speed is the frequency of the required voltage. In Nigeria, I imagine it's 50 hertz. Multiply that by 60 and divide by the number of pole pairs. A motor pole is the three-way electromagnetic windings in the stator of the motor. Slip defines how a motor is configured. Is synchronous or no load speed minus the actual load speed, full load speed. Slip, another way of doing it, slip is either expressed as a RPM, or you can express slip as a percentage. And the percentage of the synchronous speed or no load speed minus full load speed divided by synchronous speed times 100. That gives you the percentage slip. Induction motors are designed for a slip of between 5 and 20%. We'll talk about how the slip happens when we look at the torque speed curve in the next few slides. Induction motors with a slip of 5% or less are called normal slip motors. They're also called constant speed motors. They're called constant speed motors because the speed at no load and full load is almost exactly the same. So here we have the torque speed curve. What happens when you turn the motor on, in a fraction of a second, or almost nanoseconds after turning the motor on, we have a profile that I will cover with you now in terms of the torque speed curve. I just want to identify the axes of this. So we have current on that primary x-axis, and we have torque on the secondary y-axis. And here we have rotor speed or motor speed from 0 from start to 100%. So what happens when you turn the motor on? You start at the point, and this is your torque speed curve, where there's that pull-up torque, and there's large inertial losses at about that point. And then torque continues to rise, and torque has to rise above 2 times full load torque to accelerate, to move, to start the movement and to accelerate. And at this point, we call it pull-up torque. It then drops down, and it reaches the intersection between the load torque, and it's at that intersection where we achieve our one times full load torque. If you continue at this point, it's sort of called the breakaway torque. Eventually the motor will stall. What I'd like you to be mindful of is what happens to current. So starting your motor direct in line with no soft start, no VFD, what you see happen is that your current is somewhere between 6 times to 7 times full load currents. And that eventually drops off. So this here is your process load, your system load, what you need. And at the intersection is where you operate. And one way of determining slip, and it's trying my best to show this, you drop down at that point to your x-axis, and the difference between that and the point where your full load torque curve ended, that there will be your slip. So why is this important? It's important that we understand what happens when we start a motor. Because some loads are very hard and difficult to move, and some loads are less difficult to move. So selecting a motor with the correct design and the correct, as a result of that, the most appropriate torque speed curve will ensure that you achieve what you want to achieve in your motor selection. We have different load characteristics as well, and we have 3 basic types of load characteristics. We need to understand the load that you want to move. We need to understand the type and complexity of the load that you want to drive with your motor and with your motor shaft power. So we have variable torque, constant torque, and constant power, and we'll talk about that in a minute. Remembering that not all of them have S1 service rating, continuous operation. Some of them may operate cyclically or intermittently, and we need to be aware of that in our motor selection. Right, so here we have the constant torque variable speed loads. So what we have, and this is that's torque, that's speed. What we have is we find that the torque is constant over a range of speed. The current is constant over a range of speed. So voltage varies, and consequently power varies, and it varies linearly. So what we find here is that as we increase speed, we increase power. And that is very symptomatic of a conveyor belt. A conveyor belt is a constant torque operation. We have constant torque over a range of speeds of the conveyor belt. And what this means, this power graph, and this relationship, is that for a 20% increase in conveyor speed, you get a 20% increase in power. For a 20% reduction in conveyor speed, you get a 20% reduction in power. That is quite simple. So we look at conveyors because there may be opportunities. And a lot of times I find optimization opportunities in conveyors are because people run them with nothing on it. And with some basic load sensors or on-off switches, you can switch them off when there's nothing to convey. But running that conveyor all the time consumes unnecessary energy. So that's an optimization opportunity. But you're not going to save big. On the other hand, for centrifugal devices, we have the variable torque, variable speed type of load. And what we have here is we see that torque increases with the square of speed. And that is typically the performance we see with the current we draw as we operate this type of load or meet the requirements of this type of load. But power and the voltage increases more sharply by a cube of the motor speed. And this is one of the reasons why we focus on centrifugal devices when we do look at optimizing energy systems in plant. So for an increase in speed, we get a cube reduction increase in power. For a decrease in speed, we get a cube reduction in power. That is where the really big savings are made. We're going to talk about the ability loads and describe that. Those are used in pumps and fans, centrifugal pumps and fans. What we have in the variable torque constant power curve on the right is that we have a very high starting torque that decreases with speed and then kind of runs parallel for a while with a constant power over that range. And these are typically in the motors used for winding, tapering, pump tapering plants. I've seen them use this very often. Another type of load is a high starting breakaway torque, like we have here. High starting breakaway torque that then runs virtually constant with speed. So this is the area, and we find that these kind of loads typify extruders. You've got plastic extruders, you've got screw pumps, you've got aluminium extruders. That's the profile of that kind of load. Then we have the linear torque and a cube power relationship with speed in this load application. And these are typical in mixers, calendars, textile calendars, rubber calendars. We'll have that kind of torque load. So understanding your torque requirements, understanding what you need, how you need to specify your motor, will start to give you a greater insight into how to define the type of motor that you need in the plant. That will be most appropriate for what you need. Another element of that would be what type of drive do I need? How do I need? Am I happy with the direct line drive? So it's the simplest and most economical way. The problem with this, however, it typically requires 5 to 7 times full load current on starters. And that's a surge like that. It's a big surge. I mean, a lot of press plants that deal with automotive press plants, I've seen the cost that does to maximum power demand and maximum power demand costs.
Someone another question? Okay.
Let's carry on. So this is the red, yellow, and blue wiring from the supplier. This is the difference in countries. The main contactor, the overload, protector relay, the start to the motor. And that's every time we start the motor, we get 5 to 7 times the look current. 5 to 7 times the look current. Now, one of the things that I do as a measure of dealing with this in plant. So let me give you a very simple example. A sewing plant, clothing, apparel manufacturer. They've got lines of sewing machines. The machinists finish their work at night, they clean their machines, they load out, pack everything away, they get up, they leave them on truck, and they walk away. What does the mechanic do, or the engineer? When everybody's gone in the plant, he goes to the DB and he picks up the switch. All 200 machines go down. What does he do in the morning? He comes in, opens the DB board, and flicks that switch on. What do you think happens? That happens. Yes. So the thing, and it's really a behavior change thing, the thing that we started to do is to educate the sewing machinists that when they leave at night, switch the machine. So when they come in, they all switch their machines on at different times. I don't get that very high. I don't have that maximum. And Paul Vachen, the producer of the polo in South Africa, they had the same problem. They had presses that pressed out the body parts, the skin away of the polos they were making in the Eastern Cape in South Africa. And all these presses came out at once, kazook. And there was a big spike every time. And their maximum demand charges were huge. And then they found a Spanish development and design that instead of having all the presses go up at once, had them, they call it the snake. So they would do it in sequence. So as this press goes down, the other one starts moving. And as this press goes up, that one goes down, and the one next to it starts coming down. So when you watch it in operation, it's quite amazing. You see that cuts, type sewing. So what happened now, I get smaller blips. I don't get a big demand spike every time all the presses go down. Save them a huge amount of money. So we need to manage maximum demand. We need to be aware of the opportunity that exists in these. So that's direct to mine. There's another really nice system we have. So we have the star delta configuration, where the wiring configuration changes from delta to star configuration. And what happens is, instead of seeing this very great torque speed curve that we described earlier, we see something much lower, a spike and then coming down, really saving us all of that. That would be about 6 to 7 times full load currents. We don't have that anymore. We probably have something like 1 or 1.5 times full load currents. What we do in the star configuration, we see the current curve also taking quite a sharp spike before coming down. The problem with that is, in many cases, that spike in the star configuration is higher than the direct line full load current spike. So I'm losing my advantage. And in many cases, with the pump system, that becomes quite a big problem, and it actually switches the pump off when that happens. So it's something you need to be aware of. Star delta starts are good. They reduce the profile of the torque speed curve significantly. They reduce the amount of current drawn on the starter, but they may have a problem if you look at the current curve in the Y configuration, or the star configuration. Then we have the soft starter, and the soft starter in many cases is a cheaper option for the VFD. A lot of people install a soft starter. It's a voltage control device that applies a lower normal voltage to the motor to limit the starting current. So what it does, it starts there with that. And then as the motor starts moving, the voltage is increased to a higher level. And also ultimately when it reaches its operating speed, we have the normal speed curve. So this has been a progressive increase, and it's not 7 times full load current. So what the soft starter does, it reduces that high full load current on the starter. How does it do it? It has essentially this configuration. So you've got your motor there. There you have your main contactor, and here you have your overload relay like we have with the direction line. But here we've got an anti-parallel thyristor soft starter unit. And what that thyristor does, it chops the voltage waveform and modifies it. And as a result of that modification, it can chop it up into lower levels of voltage that we can see build up ultimately through the load current. So the soft starter also have the ability for a soft stop, which is especially useful in conveyors and certain pumps. And I've had many companies say to me, we don't have money for a VFD outfit. We will invest in the soft starter. Makes economic sense. It is a kind of an improvement that doesn't give you the range of control that the VFD does, but it reduces your starting current significantly. Then we've got the variable speed drive, variable frequency drive, or as they call it, the adjustable speed drive. And what happens here is by regulating the frequency, remember the supply frequency is 50 hertz, and this, by the way, is 50 hertz. Look at the speed there. That's 3,000 RPM, that tells me it's a two-pole motor. 50 hertz. So what this does, it controls the frequency. That there would be 40 hertz, 30 hertz, 20 hertz, 10 hertz. So you can see for each of them we have decreasing speed. And the walk speed, that's torque, and that's the speed over here. So we can see by varying the frequency, we also reduce the speed. So during startup, similar to the soft starter, a low voltage during startup, and at times not very different to the thyristor package that we saw in the soft starter. And this has become very popular. In early models, we had the VFD mounted on the motor. We have them mounted in little green dust-free cabinets on site. We have multiple VFDs. So they have become the control of choice. And many times when I go into the industrial plant and I see every motor has a VFD, I know that I just missed a good salesman as well. Because VFDs don't work everywhere, for every application. VFDs have a very specific application. And we'll address some of those. Any questions before we go into pump systems?
On your chart, you were limited to 50 hertz, but I know some countries are making 60 hertz. Yes, is there a difference for the same principle?
You say the frequency, yes, and you're having to go 50 hertz.
Yeah.
You're having to go 50 hertz.
Yeah, that will be the for like America 60 hertz. Yeah. So it will be they'll be able to do it for 60 hertz. Whatever interval.
I use 10, I went from 50, 40, 30, 20, 10. It could be fractions of that, to slow it down. We'll show you what a VFD looks like inside, so you get a sense of just the components that enable us to do that. Other than the fact that the soft starter is less expensive than a VFD, the soft starter has some limited capabilities. I'll show you that when we go into the VFD a bit later and we talk specifically about what you can achieve with the VFD. Variable frequency drives are able to be connected with PLCs so that they respond to changes in process temperature, flow, viscosity, and things like that. Where you have a limited capability with the soft starter to do that. I'll give you an example. I was working at a Cadbury chocolate plant in South Africa, and they had a lot of chocolates tanks, 65 tanks around the plant with chocolate that they always kept in a semi-viscous state. So whenever they needed to coach a candy bar, they would use it. And they had tank stirrers activated that were constantly stirring the chocolate to very high levels of fluid or low levels of viscosity. So we found that that's a waste of energy. So that tank could stand for a few days without having the chocolate used. So what we did is we found a sensor that we could set points for viscosity for chocolate. We then connected that to the VFD, so whenever it reached when it became too thick, it activated the VFD sped up, and we stirred it faster. If we were exceeding the upper limit, it would inform the VFD with a signal, it would slow down, and then slow down and consume this energy. So you can't do that with the soft start. So there are limitations in terms of process control, where VFDs offer immensely greater opportunity and voltage separation. As I said, it's also cheaper. The slot start is significantly cheaper. The cheaper option. And I don't know if you could reduce frequency in the same size of the chunks with a soft starter than you can do with a VFD. VFD, you've got the whole range to play with. Take it up a couple of frequencies where the thyristor and the gate of the thyristor has been manufactured to chop up the sinusoidal waveform in a very particular way, or a very particular chunk of size.
Wait, how is something soft data can simply be used for a constant speed application? Right?
Yes.
Yeah. Why variable speed is for adjusted speed application? A variable speed application.
Yeah.
So the VFD has a soft start application. The soft start doesn't have a variable frequency application. The soft starts are made to just reduce the current during startup. You can what it does, it reduces, it chops up the voltage waveform, so it reduces the voltage. What it does essentially is reduce the current. So you find by reducing the voltage, as I showed you, let me go back. So what the soft starter did, it started with a lower level of voltage during startup and then increased it gradually to full voltage level. What it does in terms of, for each of these, the current, the corresponding current for each of these would also change during that process. The primary task of the soft starter is to reduce that so that we don't go to that full load current we have on direct line. So in terms of that, you don't find any changes in speed necessarily that you will be able to achieve. What you will be, if you compare that to a system curve, and this typically would be a fan system curve, this curve over here, is you'll have very definite speed changes until you reach in max. And that results would be, that's what I said to you, it limits the amount of freedom and flexibility you have in the speed. The primary focus of the soft starter was to do that. The benefit is you get a degree of speed control. Not nearly as the speed control you could have with this, because I could have intermittent frequencies there where I could have a whole range of speed that I could achieve with my DFT.
Is there a rule of thumb? Is there a rule of thumb in trying to figure out the type of starter we use for our process? Because I know in some processes, direct online and be less expensive than using all these. Is there any general rule of thumbs that we need to consider for making our decisions?
Yeah, it depends on what you want to achieve. What is your need? What do you aim to achieve? And if all you aim to achieve is that high starting current upon starting a motor, then you want to maybe look at something as simple as a star delta sum. Inexpensive and achievable. When you want to start looking at other benefits, possibly controlling the speed as well, or even reducing that current of startup even more, then you may want to look at a soft start. If you're looking for greater flexibility with a focus on the frequency changes over a range, then VFD. So I would say to you, what is your need? Is your need specific to meet process demand or a process need, or if it's purely from an energy perspective wanting to reduce that high starting currents on startup, then I would look at a startup operation. In all the three, in all the options I shared with you, it's one of the least expensive. If you're using a direct line, you're incurring, do you pay a maximum demand charge in your plant? You don't pay a maximum demand charge. You just pay a construction charge. Hey. So while it may not benefit you, it may impact on the total national energy demand in Nigeria. Because imagine every Nigerian industry, because they don't pay a maximum demand charge, a direct impact. It's going to trip the power stations if everybody wants. So there's no incentive for you to make any change from direct to line because you're not penalized for maximum KVA charges, maximum demand charges. But if you had that, which is quite common in the rest of the world, then you'd have done something about it because it would have made a big difference. Your maximum demand, you would negotiate with the utility, and every time you exceed that maximum demand, a penalty is raised that lives with you for the next 12 months. So you pay that increased maximum demand charge for the following 12 months. That's very punitive. And in many cases, with companies, industrial plants I work with, the maximum demand charge could almost be the higher of the two charges compared to consumption charge. So if you're not paying for it, you can do it. But I would say in the interest of just the national grid and national power balance, consider next time you operate a motor, consider the installation of a star delta wiring configuration. Okay. There's no rule of thumb. It's very different, it's very, very specific to the plant and the type of process you have to implement.
I want to go back to the question yes, I want to rephrase it. For the PSD, we in the control panel we have provision for the potential meters. For sub-SATA, do we have a provision for that? Potential meter, to vary the speed. He was asking something about the speed, varying the speed. Do we have that in the sub-SATA?
Good everyone. I just want to ask, if you're in a situation where you have a non-linear load, which of the applications should we deploy? Is it the variable speed drive or the substarter? Just like a non-linear load like a rolling means or in a quarry.
So your non-linear load is going to contribute quite significantly to harmonics in your products. If I were to consider the option with a non-linear load, I'll consider a starter instead of a VFD. A VFD introduces further harmonics. As I said, you have the third set of fundamentals. In addition to your non-linear loads. Non-linear loads are the single biggest cause of harmonic distortion in industrial products. So you're driving a large winding motor, okay, and you want to consider a stop switch as opposed to a VFD. Why would is the winding, you see, if you look at that torque, those curves, the torque load curve that a VFD is more switched to variable loads. And you may find that if your battle is to overcome a very high torque on starter, very high torque on starter that drops down and then to a much lower level of the range of speed and power, then your need is only that starter need. So for stop starting, you may find it not necessarily much better than a VFD. As I said, I didn't worry about what's in the future of my harmonics. Okay, so we're going to look at the first of the three energy system types. We're choosing centrifugal devices. So we've got pump types. So I'm going to talk very high level to the rotordynamic and the displacement pumps. What they essentially do is they're taking fluid or they're taking water. These are then spun and accelerated to high levels of velocity as that velocity head, velocity water or water with a high velocity head passes through the diffusers, it ultimately creates a pressure head and it discharges that. And I'm going to just take the slide to show you what happens is, typically like in this end suction pump, you will find that the fluid comes into the eye of the impeller, so it goes right there. The impeller accelerates that and creates that velocity head. It will as it passes through this diffuser and leaves the pump, it's converted to a pressure head, and that is essentially what a centrifugal or a rotordynamic pump does. So we have quite a few. We have quite a few of them. We've got the end suction pumps, which is very common, and we'll account the high application of that within industry. Then we have vertical turbine and split case pumps. Split case pumps are also quite common. These are quite special pumps. Then we have the displacement pump category. The displacement pump is what we call a constant volume pump, where the water is essentially, or fluid is essentially sucked in and discharged, and discharged almost at the same rate of the speed of the energy consumption. They lend themselves in terms of control very well to variable frequency drives to vary the flow in those pumps. Here we have piston and diaphragm pumps that are very common, and some of these rotary pumps are found in most industries as well. So taking this pump discussion further, they can be mounted horizontally or vertically. Here we have the needle centrifugal pumps. We've got split case submersible, and we've got the same suction one. So pumps have different load types. You either have a static or you have a frictional head. And this describes the difference between them. If I'm pumping water from a lower level reservoir or tank to a higher level reservoir or tank, I will use the pump, and I will pump that water up there. So that would be a static head, mostly a static head. There'll be some minor friction head where I'm encountering friction in the piping leading up. These are short, large diameter pipes that will enable me to achieve that. So that's mostly a static head. If I look at the second configuration, I've got a pump, and it circulates water through a whole series of pipes. All of that is friction head. Even although at some points those pipes will go up in elevation, that's not a static head. It's all friction head. And all the water I pump is eventually returned to the pump and pumped to get continuously pumped that way. So we need to be aware of the different types of pumping loads that we get. Where you have high static head pumping loads, variable frequency drives are very limited in what they can do, and you need to be aware of those with the application of VFDs in those cases. Friction heads, and we have another slide that shows you the pump basics and the pressure flow relationship. So whenever we look at a pump curve, we plot head or pressure against flow. And for those who are not familiar with it, head is expressed in meters and pressure in kPa. And 1 meter head is equivalent to 9.8 or roughly 10 kPa. That's the pump curve. What do we know about the pump curve? What can we tell about it? We know that at this point where we have high flow, at this point, we've got very low pressure, because if we plot this to the low pressure. At the other end of this curve, we have high pressure, very high pressure, but we have very low flow, if we were to put that in. So those are the two extremes, very basic, showing you a Gardner's application in achieving that. And generally what we then do is we look at what the system curve is. And what is the system curve? The system curve are all those frictional losses. All those frictional losses that don't accrue to the pump, or the pump itself. They are resistance losses in pipes, friction losses in valves, and where the system curve intersects the pump curve is essentially our duty point. And that's the point we operate. And normally, the energy absorbed by the pump at that point is represented by the area in that curve. That's equivalent to the energy required to operate at that duty point. My question to you is, how do we vary the operating point? How do we take that operating point further up, further down, up curve, so we reach points of... Any ideas? How would we vary the duty point in that pump curve?
Reducing the diameter of the pipe.
Yeah.
Reducing the diameter of the pipe network.
But let's stop for that. What will reducing the diameter do to the flow in terms of pressure?
Increase the pressure.
So what you are saying is we can increase the pressure, and that's one way of doing it. So by increasing the pressure, we are taking it to maybe a point further up that curve. But why would you want to do that? Because there's that relationship between speed and head that says the rate of change of speed is proportional to the square of the rate of change of pressure. Okay. So by moving it up the pump curve, you're just increasing the head. And as a result of that increase in head, you ultimately need more energy to pump that. So if I take you back to the previous slide. So what we've done here, we've taken this tank and we've moved him up over here. So now this pump needs to work harder to get it up to that pump. So we've increased the head by a couple of meters or by a few kPa. Yes, so other ways you could do it. For example, another way of increasing the head would be to throttle the suction. So you put a throttle valve in a suction line, and you create greater pressure. The pressure drop across your valve, but also you have greater pressure. You're moving it up that pump curve. We want to try and move it down that pump curve. That's how we optimize the system. How can I achieve my process flow at lower pressures? So you're looking at regulating your flow. You would increase the flow, or you keep it constant. It's another way of doing it. So there are a few ways that you can address that. You can look at the friction losses in your system and remove some of those friction losses. Find out why they are there and take measures to reduce them so you have frictionless flow, or maybe less turbulent flow and more laminar flow. Those are some of by having less spikes and bends in your configuration. Those are some of the solutions. Go through them very quickly. Modulating control, rotary on-off, reciprocating on-off, and variable frequency drive. I want you to notice that at maximum load, that's loads, and that's power. At maximum load, there's really no benefit amongst it. They're all quite efficient. With compressed air, your biggest challenge is how do you manage partial loads. So how do you manage your compressor between 30% and 80% load? That's where you start getting these big discrepancies between the different control systems. And what this shows, without getting into great detail, is that you look at the power requirement for partial loads for variable frequency drives, they're the lowest of them all, at 20%. You see that we have for reciprocating on-off control, 40%. We have rotary on-off, maybe 45%. We have modulating control at about 70, 75. So, partial loads. Managing partial loads in your compressor system is where your biggest challenge lies. Not at 100% full load, it's at partial loads. And running and operating your compressor at partial loads is highly inefficient. Like we handle motors, highly efficient, below 50% loading. So what are the strategies in compressed air systems? One of the largest wastes of compressed air is compressed air leaks. I walked into an automotive plant, the old press plant, and I stood watching these presses, and as I stood, I felt the cold breeze on my ankles. And I said to my colleague, "Do you realize there are a lot of air leaks?" He said, "Yes, we do." I said, "Then what are you doing about it?" He said, "We are too busy, we can't stop the plant." I said, "My friend, you are never too busy to save the kind of money you're throwing away here." So leaks is a big thing. In fact, leaks is so important that the Toyota plant in Japan employed a team of engineers and technicians. And their job is nothing but fixing leaks. So they start at one end of the plant in January, they work their way through the plant, fixing leaks, and by the end of the year they come back and start again. Because Toyota just don't realize the cost of the losses as a result of leaks. We find that in an average plant, the compressed air leaks can be as high as 30%. Telling you now, you don't believe me, go back and check. And I'll show you two ways of measuring it. I was at a wafer factory when we couldn't understand the loss of airflow. We had flow meters on the header coming out to both of the compressor room. They had 5 compressors. But measured, we had flow meters further down in the void and we had flow meters further back on the dispatch lines. And when we added up the flow meters on the dispatch lines and the void, we had a big gap. There was some airflow that was not accounted for. We discovered that their air leak losses amounted to 40%. They didn't even know that. But guess what? They wanted to buy another compressor. So air leaks is a significant problem that you need to be aware of, you need to manage. And I'm not saying that you need to get your air leaks down to 0. If you can get your air leaks down to 10%, I'll shake your hand. Because that's life, that happens. And very often I find that we fix up air leaks and then we pat ourselves on the back. We think we've done a good job. You've done absolutely nothing. If you are going to fix up the air leaks and stem the air leak losses, you need to go back to the compressor and change your settings. Because all you're going to do if you do nothing, that air is going to find another weak point in the distribution line and cause another leak elsewhere. So you're going to benefit by fixing up air leaks, by reducing the pressure of compressed air generated. Okay, so the second point is alternative methods. I've spoken about an electric blower. And you don't interrogate that. In a large knitting plant, I found that they had an air line onto the dial of the knitting plant, just unclogging fiber and lint so it doesn't clog up the feeds to the knitting machine. And I asked them at what pressure they were doing it, and they said 4 bar. And I said, why 4 bar? Who told you 4 bar? No, the Italians told us 4 bar. Because the Italian knitting machine. And I said, let us look at the manual. Is it really necessary? I said, have you tried it at anything lower? And they said, no, not really. So I said, let's engage with the supplier of the knitting machine and find out if we can drop that to 2 bar. Still achieve the cleaning of the feeds into the dial of the knitting machine, but using less air. We saw the relationship between electricity and compressed air. Compressed air costs 7 times that of electricity, and we can reduce that pressure, we can certainly reduce the energy demand. Over time, the supplier said, fine, let's try it, but do it half a bar at a time. And they did it. I was working at a clothing plant in KwaZulu-Natal in South Africa, made men's shirts for export and local market. And they had 2 compressors, rotary screw, oil-flooded rotary screws. They were operating them at a load control, and they were generating 7 bar compressing. I went to the sewing machine, I went to the actuators, I went to all the areas they use compressed air. And I found that the most they needed was about 5 bar. So I allow, very generously, I allow for a pressure drop from the compressor and the main header to the machines in the plant. I allow 1 bar. So if the machines need 5 bar, and we have a 1 bar pressure drop from the compressor room, I shouldn't be generating air at 7 bar. So I went to the mechanic and I said, I was visiting the plant once a month. I had a student there, an intern that I was mentoring. And I said to the plant mechanic, I said, do me a favor, drop the setting by a quarter bar and phone me. Now, I'm not saying he'll do this because I would never do this. He dropped it by a quarter bar. He called me and he said, nobody's complaining, everybody's happy. I said, have you operated all your machines? Have you been operating at maximum load? He said, yes. In fact, we did. He said, do me a favor, drop it by another quarter bar. Dropped it by another quarter bar. Called me back and said, things are fine. So I had a meeting at my next visit. I went and I met the plant manager. He wasn't very happy that I did that. But what I proved to him is that something he didn't want to do was to reduce the pressure of compressor generator, which was way too much. Didn't affect his production, didn't affect his quality, didn't affect his output, didn't affect his productivity at all. But he saved him an enormous amount of energy. So those are some of the barriers we encounter in plant, that people just refuse to do it because they've been told not to do it, or they've done it that way for the last 10 years of their lives. And as an energy manager, you need to work around some of those. I would never do it again because things could have gone wrong. But the point I proved at the time was you didn't need 7 bar. But I satisfied myself by checking the machine manuals, checking the machine specification, checking that indeed they were generating at what the compressor indicated was right there, pressure gauges, independent pressure gauges, that we could do it with a very low risk of danger, and we achieved it. So normally in plants, I find that operations always want as much air and as high as possible pressure. That's nice, but it can be wasted. So use the lowest system pressure possible. That's the lesson I can share with you. And fight pressure losses. Keep them to 9 meters per second. I know. How are you going to measure compressor velocities? But the higher your velocity, the higher your friction loss, the higher your pressure drop. So this is the rule of thumb in terms of compressor piping design. At the compressor, you want to achieve a maximum of 5 meters per second. On the header, the compressor header leaving the compressor room, you want to achieve a maximum velocity of 10 meters per second. And at the drops going down to the machines, you want to achieve a maximum of 15% meters per second velocity. To achieve a desired pressure drop of 4.15 bar between your compressors and your end users. Now, one of the first things I do when I get to a plant with a compressor system, I would go into the compressor room and check what they operate in. I'll check what the pressure is that they're generating compressor at. I would then go to the furthest point where they use compressor, and I would take the pressure reading there. If they don't have a meter there, I'll take the pressure reading there. And that gives me the pressure differential. It gives me the pressure gradient of that system. And if that's more than 1 bar, then there are some opportunities. Opportunities to look for areas where there are pressure drops. Pressure drops occur sometimes because of different piping diameters. You could have losses along the way, the compressor leaks as well. You could have other barriers to airflow that would cause pressure drops. So consider that as a good rule of thumb when approaching a compressor system in a plant. So I inserted these last night because I wanted to leave you with this understanding. This is a very good It's a very good methodology to determine what your compressed air leaks are. So in this first one, if you are a plant, and there are many of the plants you're going to see in the next week, that operate 6 days a week, 5 days a week. That means your plant is idle at least 1 day a week. Then on that day that the plant is idle, I want you to go into the plant with your mechanic, with your engineer, with your manager, and make sure all the machines are switched off. All the machines that use compressed air are switched off. What you then do is you start up your compressor and pull until it's completely loaded, fully charged, distribution line, receivers. And then time that. And then you wait. And the leaks will start using up that air. And the leaks will start using up that air to a point where the compressor starts up again. You time that. And you do a few cycles of that. And that gives you the information to calculate your compressed air system loss. So we will use this formula here, which is the leak volume. This formula over here. The leak volume in cubic meters per minute is the volumetric flow rate in cubic meters per minute times the time download divided by the time load plus the time unload. So let me express that to you. We've done some measurements and we found the volumetric compressor flow rate is 3 cubic meters per minute. The time of loading, we did 3 cycles, was 120 seconds. The total measurement time was 600 seconds. So 3 times 120, and I'm over here right now, divided by 600 is equal to 0.6 cubic meters per minute. So this plant has a 20% leakage. You may not have the benefit of having a high day a week. You may want to consider doing this when you stop for maintenance, or consider this another time, or consider this one. So here we measure leak losses by exhausting an air receiver. So what you do is you charge this air receiver, and you will have a pressure meter on your air receiver. So you charge this pressure meter, and I would recommend that you charge it as high as possible. You note that. Make sure all the machines, make sure that no air being leaked out, air being leaked. Yeah, there's leaking lots of compressed air, so we want to make sure that there's no tools being used, there's no air being used by any of the tools whatsoever. And what you then do is you time the time it takes to reduce that from the pressure level you had to the new pressure level. And I suggest you take it down to about half of the original pressure. Why? Because as the receiver drops its volume, and as the pressure drops in the system, the leaks run out slower. So once you have this information, and by way of exercise, that's the formula that you will use to determine your leak losses. If we know that the receiver volume is 0.5 cubic meters, the pressure at the start of the exercise was 9 bar gauge, and after 3 minutes it was 7 bar gauge. You apply that to the formula, and in this case, the leaks with 0.33 cubic meters per minute. So it starts to give you an indication of the leaks you have in your plant. Once you know that, because people always talk about, hey, we need to fix the leaks, but nobody knows how big it is, and how much it's costing you. Once you know that, you want to multiply that by the cost of generating one or creating 1 cubic meter per minute of air flow. Then you can present a financial number to management to say, you know what, our compressor leaks about 30%, and it's costing us maybe $500,000 a year. We need to do something about it. That's more compelling than simply just going and talking cubic meters per minute flow. How do you determine the cost of the compressor? In many ways of doing it. Take the cost of the electricity absorbed by the compressors and take the total, if there are multiple compressors, the total flow generated at that given pressure, and do a very rough number on the cost per cubic meters per minute of compressed air, and use that to apply and quantify the losses. So some of the energy strategies in compressed air system: install intakes. When I say intake, I'm talking inlet valves. Install intakes in locations providing the cleanest, driest, coolest air possible. Now listen to me, this is not a empirical point, a factor, but it's a good rule of thumb. For every 4 degrees Celsius drop in air inlet temperature to a compressor, you improve the compressor efficiency by 1%. Every 4% Celsius drop in air intake improves the compressor efficiency by 1%. I had a client who had his compressor right next to his boiler, and that's not uncommon. I see a lot of plants where the compressor plant will be right next to the boiler room. Boiler rooms are hot by the very nature. What we did, fortunately, was not too far from a perimeter wall. We knocked a hole in the wall and we put a duct in where it could then draw in colder ambient air, more dense ambient air, and improve the efficiency of the compressor. Because when you have hot air to air inlet valve, what essentially you have very rarefied air, and your pressure is gasping for air, because we need that dense air. The more dense air we can get, the greater the compression of that, the greater the quality of compressor produced. So that choose filter systems with the lowest pressure drop. And the filter systems we speak about here are the filter systems we looked at right at the beginning when we looked at these. Make sure you have the lowest drop across these filter systems. Many people will have double filters. And a good way to just keep a little eye on that, to track your filters, is to have your filter reading that shows, the green and the red little reading on each filter. When your filter is clogged, it will be in red. If it's green, your filter is clear, and passing it through. That makes a very easy identification of problems. Choose filter systems with the lowest pressure drop, and compressors give up high volume with low grade waste heat, which can be used efficiently by some industrial plants. There's a company right now in Sri Lanka that's capturing the heat from the rotary screw compressors, and they're using it to heat up their boiled feed water. A lot of the newer versions of rotary screw compressors now come installed, fitted with a waste heat recovery opportunity. I've worked in a wood joinery plant that makes doors and window frames, and they use the heat of compression to warm up the factory in winter because it's very cold where they were in winter. So use that heat. 80% of the energy absorbed by a compressor is generated as waste heat. And if you can capture that heat in any waste heat recovery, it could be heating processed water, it could be heating hot water for the staff instead of using a heat pump or a geyser. Those would be the benefits that you can certainly gain. And Michael, are we ready for time?
5 minutes.
5 minutes. Okay. No, but I think I'd like to start this one so we can think about it over the key. Variable frequency drives, variable speed drives. So when you open up your VFD, this is essentially what you're going to see. So what we are seeing here, these are the line voltages coming in. And because they come from really good power plants, great turbines and generators, they are very clean and they sinusoidal. So we have 3-phase AC input voltage coming in, 3-phase to those. It goes into that's the VFD. So what it does, when it comes in here, it goes into what we call this rectifier circuit. From the rectifier circuit, it goes into these two areas. What we have here is a capacitor, and we have a coil. And then it goes into this power transistor. There's a filter system, power transistor, and the resistor. And what this does, it chops that sinusoidal voltage up into as close to the DC voltage as you can get. And at this point, those voltages are now being transformed to this. We do that because your controlled speed in a DC voltage is much easier than in an AC voltage. So once we do that, we are able to control the speeds, and it passes into this inverter circuit over here. This is the inverter circuit. From the inverter circuit, it goes out to your induction motor. The waveform at this point going into your induction motor looks like this. It's returned to a form of a sinusoidal wave, similar to what we had in the input, but not exactly, because we now have this pulse width modulation here. We had to do a lot of pulse width modulation to enable us to reconfigure the waveform. The result of this pulse width modulation is harmonics. And that harmonics will destroy a poor motor. So what we want to do is to install a filter over there to protect our motor. And that is really the very broad, high-level explanation of what variable frequency drives do. They convert sinusoidal supply waveforms, they chop it up into a DC waveform, they vary the speed as required, they pass it through an inverter, where with pulse width modulation we reconfigure the sinusoidal waveform and send it to the motor. And we slow the motor and we speed up the motor, depending upon what the demand requires. That's in a nutshell your variable frequency drive. The benefits of VSD is large energy and cost savings. And really, I saw a number yesterday where you were showing a 70%, 69% saving. 69% saving with the application of VFD in a centrifugal device, in a fan system, removing the damper and slowing the fan down. And that was significant savings. So VFDs are a better match for machine to process requirements. So if your process is fluctuating, you want to be able to have a supply that moves with it. When you have multiple compressors, when you have multiple pumps, when you have multiple fans, you don't need a VFD on every one. You need to decide which will be your base load compressor, your base load pumps, your base load fans. And make sure that you use one. In the old days, we used to look for the smallest one to be our trim fan, or trim component. Today, we look at one of the largest compressor, and we make that the VFD compressor. And that then trims the supply to meet the process demands. Just the technology and the process has changed. The other benefits of the VFD is better start and stop control, pretty much like a stop-starter. Reduce starting current significantly, as we showed you. Reduce stresses on the system and reduce maintenance along the line. But there's always a what if. There's always a trade-off. As good as this VFD is, you need to consider some of the practical applications. If you don't have the money, try the soft spots. If you can't reduce the speed because the process doesn't need it, then don't worry about a VFD. If there's very little variation in process demand, if you're producing biscuits, heating up water, if you're producing product 100% of the time, all the time, like this breakfast wafer plant I spoke about earlier, you don't need a VFD. Your load and load compressors will run more efficiently at near maximum load than VFDs can. The VFD range is only 60 to 80, some say 60 to 90%. The sweet spot for VFD compressors is roughly 70 to 80%. That you want to be running your VFD and maximizing the performance. When you have a load requirement or a constant load requirement higher than that, 90 to 100%, I won't put a VFD in to do that. I will simply run that with my load and load compressor. Consider associated equipment that do not allow speed changes. Sometimes you are limited by process equipment that can't fluctuate, can't vary, and you may be limited by using VFD in those cases. In pump systems, you've got a very large static head. Your VFD can only operate above that in the friction area. Can't operate within the static head. Harmonics. You need to be aware that you have equipment that is sensitive to harmonics. You need to stay away from the VFDs. So what are some of the practical considerations for VFDs? And I wanted to share this with you. To me, that's one of the big ones. No dust, no humidity, clean, cool environment. VFD is thriving that. You're going to subject the VFD to any different conditions, it's not going to function properly. The other big consideration would be this one here. Suitable cabling and electrical filtering. You don't want your cables to your VFD longer than 5 meters because of some of the losses and the replication of the mirroring of the waveform in that cable. Big problem. So you want to certainly take note of those two. So let's summarize and just talk about everything we did since we started today. What are some of the opportunities? You got some handy guidance and tips on optimizing some of the systems. Let's look at just some of the more general motor systems optimization opportunities. When it comes to deciding whether to rewind or whether to replace, you need to develop a motor management policy that defines that, so that your procurement officer knows that, so your plant engineer understands that, so your operations manager knows it too. So many companies set a threshold dependent on the cost of rewinding. They set a threshold where they will say, we will not rewind a motor smaller than 11 kW. Some say 50 kW. You decide that based on the cost of rewinding and the quality of rewinding. So when a motor fails that is smaller than that, procurement knows they can replace. And there may be another directive to procurement that when you replace a motor, replace it with an IE3 motor. So this is part of what I call your motor management policy. If the motor is larger than that, you want to then get quotations for rewinding. You want to find a reputable rewinder and make sure you go and visit them, you have a look at their ovens, you have a look at the quality of work they've done, you get some references from other companies on them, and you then use them. It's usually more cost effective to replace small motors than to rewind. Different organizations have different maximum thresholds. Rewound motor efficiencies vary. A good repairer will return it as per the original condition, and a slightly worse or not so good repairer will give you your motor back with an efficiency of 2% less efficient than when it was when you bought it or before it broke down. Okay, so slide 77, we're going to stop here. It's a good time for lunch. Think about what I said. We can take some questions. It's a 30-minute lunch, right? 30 minutes? 30 minutes. Okay, so we come back. It's now 11:45, so let's come back at 12:15, please. Because a very good discussion on steam afterwards. Thank you.
So 20% is finished. Sorry, 20% is finished.
Was replacing that motor with an IE3, and that gave us the single biggest benefit. So you can do these numbers instead of just simply saying, I'm going to rewire or I'm going to buy a new motor. Do the analysis and compare that with other options you may have. And have your vendors work with you, make them your partner in this to make and reach informed decisions like that. There are opportunities in maintenance that could improve your energy performance. Don't discount that. With maintenance, you are using your OPEX budget. You don't have to ask for more money. You're using what has already been budgeted. And you're being clever about them. You'll always have a lot of jobs in maintenance that's seeking to do some work. Prioritize those tasks that will impact your energy performance. So if you want to look at shaft alignment, you want to make sure that if you look from the top and you look at your motor, that your shaft is aligned in a way that doesn't cause any undue losses. You want to look at lubrication. And remember what I said earlier, too much lubrication is as bad as too little lubrication. I have people thinking that they can have as much lubrication as great. It's not great. I've seen the damage it can cause to some bearings. Under heat, with too much lubrication, more dirt is attracted to the lubrication, more then gets into the bearing. So you have to be quite specific about your lubrication in terms of the quality of the lubricant, the amount of lubrication, and your lubrication cycle. Dirt removal is important. I was in a shoe factory in Yangon. They were making hush puppies for the Japanese market. And I went into a section where they were grinding the insoles. They were grinding the sides of the shoes. And I couldn't see the motor for the love of money. And when I scratched beneath the grinding machine, I found an electric motor covered with rubber grindings. How that poor motor will ever survive, I don't know. But dirt removal, keep them clean, keep your motors clean. Sometimes we also become too clever for our own good. I was at the Volkswagen plant in Uitenhage in South Africa when I walked into the assembly where they were assembling the VW Polo motor cars. And I noticed that every motor had a shower cap on the fan end of the motor. And I said, who decided that? And they said, our manager from Germany. I said, why? They said, it's dirty. I said, does he know why we have a fan? He just blocked the airflow to cool the motor. All those motors were operating at higher temperature than designed. So sometimes people do stupid things. And maybe they do it for other reasons, they get energy. Or they do it not knowing what they're causing. I think we need to be very mindful of that. I was at the dairy in South Africa when I noticed that there was a lot of waste heat and they processed near to the boiler house. And I said to them, guys, you are doing some chilling. You could use that low-grade heat and drive an absorption chiller. Absorption chillers, 2-bar steam would be good enough. They are very low COPs. They don't have high COPs. They're very below 1. But you're using waste heat. And I said to them, why aren't you using the waste heat in your weighing to produce your weighing? And they said, no, we did a calculation and it's not economically viable. I said, okay. When did you do that calculation? No, we didn't do it. Blackie did it. Who Blackie? Blackie is our maintenance manager. I said, can I speak to Blackie? No, he retired and he died since. So they were still doing what Blackie told them to do. Cost have changed, steam flow has changed, cost of absorption chain has changed, technology has changed. We're still doing what Blackie told them to do. So we call it the one. There's my colleague in the States, Hilly, has a good description for it. He called it the one failure wonders. And I worked for 11 years at the Council for Scientific and Industrial Research in South Africa. And we were tasked to improve the chiller systems we had for our conference centers. We had very large conference center facilities, many conference centers. And we had done our analysis. And what they were doing up until that point is that they were keeping the conference center closed about the first week in December, and it reopened about the second week of January. There were like 12 large conference centers. It was 2-level building with a big kitchen and everything else that goes with having a conference center. And they kept the chiller system running over that time. The first week of December and the second week of January, nobody in that place. So we went to them and we said, why are you doing that? We can work with you. We don't have to switch off all the pumps. We can keep one pump recirculating to avoid rust buildup. We can certainly switch off the fans. We can really save a lot of energy. And what we do, just before we come back, a week before we come back, we can come and test the system to make sure it's okay. And they said, no, we can't do it. We can't do it because 7 years ago, we couldn't restart the chiller system after the Christmas break. And our first conferences were done without air conditioning. So, what I find is that people in companies lock onto a failure, and that becomes the reason for not wanting to change. Those are the barriers you will encounter. be aware of it. Ventilation, voltage balance. Voltage imbalance is quite a major issue in terms of power points. Make sure your voltage, your phase is balanced. Harmonic filtering becomes an opportunity to save energy in terms of maintenance. You know, if you've got a thermal imaging camera gun in the project, it's a heat micro. FLIR produces some of the best of these instruments, but we use this to detect thermal hotspots. We do use this to detect breaches of insulation in steam boilers. We do this to check in chilled system or refrigeration lines, heat gain along the pipeline or within vessels. We can use it equally well in a motor. Have a look at that picture. Have a look at how hot that is. And imagine somebody took a shower cap and put a shower cap over that. That's the kind of thing that you need to be aware of. And we can certainly become more aware of them if we regularly check them. And I'm saying is, take ownership of your plant. So acquire a thermal imaging or IR camera. And they're inexpensive today. They used to be very expensive items, and you still get some very expensive models. But you can get this for a relatively low cost. And make sure that you take regular checks of the main motors in your plant to determine whether some are running hotter than others and why they're running hotter than others. And what are the temperatures? Because this will normally give you a scale of colors from red to yellow to green to blue to purple. And it will indicate the temperature range for each. So you will have an indication of how hot your motor is running. And be proactive and take steps. If you don't want to do it, you can outsource this to a consultancy to do it for you. But I don't believe, I think your first port of call is do it yourself. And if you don't understand it, you can call in the consultant to guide and discuss it with them. But these are opportunities, and these are early signs of maintenance issues that says it may lead to failure. Vibration analysis. We've got a vibration tester in the kit of field measurement equipment we bought for the Nigeria project. And in that we've got a vibration analysis. You take the vibration meter, you keep it against the housing or the casing of your motor. If you can touch on the valve without causing problems, you can, on the bearing, you can do that as well. And what these give you, many of these meters will give you a color-coded indication of the level of vibration. And as I said earlier, bearings are one of the biggest causes of motor failures. So if you could detect early failure in bearings, you are saving yourself the opportunity at the next of having to stop the plant. And what you can do is at the next available stop, you can replace that bearing without any further disruption to your operation. I had an old engineer at Volkswagen in Houston, South Africa, who came to me after we had delivered a 2-day training course within the plant on motor systems. And he said to me, he said, you know how, these things are nice, they're all fancy, but I still do it the old way. He said, I walk down the line, the assembly line, and I touch each of the motors and I feel the temperature and I listen to the bearings. And I'm able to detect them because I know the sound. I'm accustomed to the pitch and the sound. That's great. But not many of us see many old people, many experienced people at plants any longer. This is equally effective. This is a bit more scientific. Transmission belts. You know, flat belts and V belts are not as efficient as synchronous belts. But also when you have a synchronous belt, you want to know when it's starting to wear. And we want to make sure tension them correctly. So what you want to do with them is you can use a very simple meter to determine whether the tension is ideal. You can also use these profile gauges over here to determine whether these edges here are becoming round and whether they're becoming thinner. Because these guys do offer any saving opportunities. And it's something you may want to consider. So where do you want to look first? What are the things you want to focus on first when you look to seek to optimize your motor system? Large equipment with high use. So large motors that run 8760 hours a year, 24/7. Equipment that has long downtimes. The downtime because either it's broken or downtime because there's no need for it. Systems with varying duties or outputs. You want to look at auxiliary equipment that's not critical in the production process. And sometimes a lot of energy is consumed by auxiliary equipment that nobody worries about, but they are impacted by what happens in the plant. Problem equipment and systems with high failure rates you also want to have a look at. Where you don't want to have a look at. You don't want to waste your time by looking at process equipment where the value of the group is too high and the company is not willing to take the risk of a failure. Whatever you do results in a failure or a stoppage, it can really kill the profits for that month of the plant. You also don't want to look at critical processes. It is not worth it, so high risk. Stay away from them. Just as an example, you don't want to do a motor systems optimization and a sealed compressed air unit. You don't need compressor. And it has a motor, and you will find that motor in that compressor generally would be very efficient, be well designed, and it would be appropriate for the need. You don't want to look at small equipment because the savings will be small, and you don't want to look at equipment that's about to be replaced or upgraded. So some of the questions I often ask when I get into a plant to do an assessment is, are you planning any changes? Are you planning to add another line? Are you planning to relocate the plant to another location? I don't want to waste my time looking at optimizing your system only to find out that you are moving, or you're downsizing, or you're expanding. The other thing I often do as well is I try not to do my assessment in a seasonal plant when it's off-season. Off-season, your motors are not under strain and stress. Off-season, your compressor is not under stress. I want to do my assessment during peak production. Because during peak production, that everything is under severe strain. Maximum load. I want to see how your motor compares, how it performs, whether your pump meets the requirements under peak production. So very often, people didn't understand it when they asked me to do an assessment on a plant, that I would decline it because the period they've given me for the assessment just didn't make sense. I wouldn't learn much from that. In fact, nobody would learn much from that. I want to see the plant really push the limit, to really get an understanding of how well it's designed. Because when you size a motor for peak requirements or peak load. Now you may operate at peak load 5% of the time, 10% of the time. But you need to size a motor to cater for peak load. So when I do my assessments, I want to be in the plant when we are touching peak load. What are the actions you can take? You can upgrade the motors from IE0 to IE3. We can switch up. There's a lot of switch up options. We look at that on the next slide. We can look at VSD opportunities. What are the opportunities to slow down centrifugal devices and equipment? We want to look at optimizing the system. And so often as engineers, we just think engineering concepts. We don't take the time to go into the plant and see how are they making these peanuts, how are they making these biscuits, how are they making these garments, how are they producing this steel, how are they producing this packaging, and see whether there are opportunities to optimize that process. Switching on, you want to switch on during tea breaks. Or there food products, and I noticed we have a lot of food products companies in this room. I was at a food products factory in Yangon, and I was watching some logs being delivered, and there are all these band saws busy cutting them up into board. And while I stood there, the bell for tea time went. And without finishing, all of the band saw operators just left the machine and went to a nobody bothered to switch the machines on. a very simple educational opportunity to change that behavior would have made a big difference. And eventually it did. You are reduced to times, time switches, tool changes between batches. But be aware, you can't switch every motor on and off as many times as you want to. There are limitations on that. And these are specified by the vendor, but especially large motors. A large motor you may only be able to switch it once or twice in 24 hours. So be aware of that. How to switch it on, educate people. To me, that's my first choice. Training, training, and retraining, and refresher training. It's the most inexpensive thing. I don't have to buy any equipment, I just have to convince people of the importance of switching off. If they don't listen though, and it's costing me money, then I will look at timers. I look at timers, maybe alarms to remind people to switch it off. Thermostats, interlocks, load sensors, so there's nothing on your conveyor, the conveyor stops. Process control. Transmissions, we just spoke about that. Look at loose belts, loose D-belts, loose flat belts. Look at motor shaft alignment problems, bearing failures, oil leaks in the gearbox. Look under the gearbox, and there's a little oil panel there, or piece of oil. You know there's a leak, and you know that there's a need to improve maintenance. Listen for noisy gearboxes and screeching pulleys. So use the senses God gave you, your eyes, your ears, and your touch. And not only in motor systems, but in all energy systems, especially in steam systems, they can really enable you to detect early signs of failure. Then we have a work example that I want to go through with you to show you just the D&D saving opportunity. And as it happens, it's not very different to what I saw with yesterday. So what we have here, we have a pumping system, and the motor was running at 2,900 RPMs. How many pole motor was that? Anyone? 2. 1 pole pair, 3,000 divided by 1 is 3,000. So we have slip of 100 RPM. Electrical power, 22 kW. Pressure in this pumping system is 4 bar. We have found an opportunity to reduce the flow by 50%. What do? We now determine the new speed, the new motor speed, where we had 2,900, we multiply. Remember our affinity laws? The change in speed is proportional, change in flow is proportional to the change in speed. So our flow rate reduces by 15%, so we multiply our 2,900 RPM by 0.85, and that's the change in speed as a result of that change in flow. What's the new pressure? The affinity law says the relationship, the change in speed is proportional to a square of the change in pressure. So we apply the affinity law, it was 4 bar. So 4 bar times 0.85 squared. So the pressure reduces to 2.9 bar from 4 bar. But then we look at the power. This is a 22 kW motor. The affinity law says the change in speed is proportional to the cube in the change in, or change in power is proportional to the cube of the change in speed. So we have 22 kW times 0.85 cubed gives us 13 kW. We need to discount that because by installing the VFD, we're going to incur some losses of between 5 and 6%. So we will take 5% to account for additional losses due to the VFD. So our 22 kilowatt motor minus 13.5 multiplied by 0.95 to account for those losses gives us 8.07 kilowatts. So a 15% flow reduction gave rise to a 37% power reduction. That is the value of VFDs in centrifugal devices. That is why we look at centrifugal devices and why motors play such a big role in that. I can't stress the importance of sub-metering because without that sub-metering, we have very little basis for proving our savings. But I must also add that we need to be strategic about sub-metering. So when I do compressed air training and I do compressed air assessments, I always find that the students, the young engineers, want to meter everything that flows or changes pressure, current. That's not really necessary. You can be very strategic about that. You can look at the exception or the critical measurements and decide what it is you want to measure. And from that measurement, whether you can make deductions about some of the other consumptions in the plant in terms of using energy in the mass balance. So sub-metering is critical. Sub-metering is the budget, but here's the art of sub-metering. If I go to my manager and I say to you, can I have $50,000 for this meter? He'll say to me, so what is it going to save me? I can't prove that that meter is going to save anything. It's going to be a hard job to prove that that information will help you manage the plant better. So what do? Is when you have the opportunity to install a new piece of equipment, a new boiler, a new compressor, a new pump system, a new fan system, is insert the metering adapter, because the relative cost of your meter is small compared to the cost of your energy system. And the boss will sign it off. It's not a big deal. But when you go later on, 2 months later, and you then ask for extra budget for the meter, you're going to have to argue the point, and you may not convince him that it's necessary. You may not see the benefit, the indirect link. So you need to be strategic about metering. But your point is well made. Sub-metering is important. Don't always look to sub-meter things where you can use proxy measurements. So let me give you an example of a proxy measurement. We're going to talk about boilers now. I don't have a steam flow meter because steam flow meters are expensive. The cheapest steam flow meter I can buy is an orifice plate meter. A vortex shedder is expensive, and a Coriolis meter is even more expensive. Well, I know in the boiler, if I do a mass balance, that the feed water into the boiler is equal to the steam out plus the blow down. Blow down is a small amount, steam is a big amount, boiler feed water is a big amount. We can discount the blow down, but we can include it. If we know that blow down is normally expressed as a percentage of feed water, so I can determine my steam flow, steam generated, by simply looking at my water meter from the blow down and factoring that, my water meter from the boiler feed water into the boiler, and factoring that by the blow down percentage. Gives me an indication of my steam. I didn't need a meter for that. I'm applying mass balances and energy balances. And we have that challenge. You're not the only one. The challenges are across the world. If the cost of sub-metering is prohibitive or prevents us from presenting accurate calculations on saving. But any calculation you do on saving is going to be an estimate. There will be a degree of uncertainty in that. It's not spot on 100% accurate. There's a degree of uncertainty in it. It just depends how robust you want to be in the determination of your savings. But if management is willing to affect a high order of accuracy level, then you may have to get sub-metering. If management is willing to maybe look at not such a strict and high level, you can get away with proxy measurements or energy and mass analysis.
So, before we went on break, in your discussion, you made us understand that when installing VFD, the power cable should be 1 of 5 meters. Should be 1 of 5 meters.
You're talking about
Installation, yes.
You don't want it to be longer than 5 meters.
So I'm saying, what would be the impact if it's longer?
Higher I squared R losses, and what you start to see mirror or duplication of the sinusoidal waveform on the length of the cable. And it starts to cause quality issues, overheating, and things like that. Losses on cables are huge. You can't believe the effort that goes into a plant when deciding where to locate a transformer, because of the losses along the length of this cable to the plant. So, length of cable is a critical element in containing cost and maintaining power quality.
So my second question is, you said the motor is not supposed to be, has limiting way of switching them off. It's not advisable to switch motor off, especially the high capacity motors, more than twice a day. So I'm saying that happens. What is the impact on the motor?
It won't change that. It will just stay off. So if I've got a big motor, a 500 kilowatt motor, half a meg motor, and I've switched it off, and now I want to switch it back on, it just won't come back on. You need to be aware that for each of your motors, especially your large motors, what this maximum number of switch-offs are, or what the interval between switch-off and switch-on should be for years. And that will limit that. So when I get to large compressors, I don't switch them off because I can stop the plant. I'm very wary of that. And I want to find out when last time I switched off as well. Because I may come there a few minutes after it was switched off, switch back on again. So you need to be very careful of that. It can cause some serious interruption issues. But check your vendor manuals, your vendor technical specifications for your motor. It will specify that very, very clearly. Does that answer your question? Thanks.
Another question?
Yes. I just want to ask a question related to the harmonics.
Harmonics, yes?
Yes, on the BSD.
Yes.
I just want to know if harmonics are not harmonics attenuations. Attenuation is not inbuilt in the drives.
Say that last bit again.
If harmonic attenuation are inbuilt in the drives, so that we minimize harmonic generation.
It's not imbued in the drive so much as it is imbued in what happens in the inverter circuit in the drive. Because the inverter circuit now aims to take that DC waveform and generate a sinusoidal waveform. And the way it does it is with pulse width modulation. And that generates harmonics. The pulse width modulation in the inverter section of the drive, BFD, that's the cause of the harmonics.
The question I'm asking, is there any no circuit within the drives or outside the drives that can bring about minimization of the harmonics interference?
The only thing we do is we put an active filter, a harmonic filter at the back end of the drive to eliminate those third and seventh fundamentals from going to the motor and eventually going into the parts. So we filtered it out. We want as clean a sinusoidal waveform coming up. We want to mimic the quality of the sinusoidal waveform that went into your BFD. So we need that pulse width modulation to do it. There's not been a solution to that yet. So all we do, we contain that. We contain that with filters and chokes after the BFD to prevent that affecting the motor and burning the motor out. Thank you. Good.
Yes, I think somebody mentioned, you mentioned something about switching, talking about switching on and off of the motors. If you consider the nature of Nigeria, like, we have erratic power supply. So, in most cases, we always experience that. So, what are we going to do to stem this, to stop all this kind of thing?
Yeah, it's kind of case-by-case response, and I would answer, but the thing that I would do is I would identify the critical motors in your plant. And I would maybe have a generator supplying those critical motors in an unaffected plant. The other motors that are very good, sorry?
Many of them considered
Yeah, that one is happening on land. We we run some motor generator to the
Yes. So, in fact, I was about to say that companies that use those big rated models, they usually don't put those motors on grid. Instead, they put them on their generator, either turbine or generators. So, it's not, it doesn't really make sense to put
So you're saying it's not, doesn't make sense to put them on the generator?
Yes, because on the national grid.
Oh, not, yeah, so we don't put them on the national grid?
Yes.
Rather like you know.
Yes, I don't see because.
Okay, thank you.
Okay, thank you. And like in our own operations,
We have some operators that may not like to experience power failure once we are running that operation. So whenever I want to carry such operations, we run on generator, on diesel, to avoid such occurrences. And again, I know that if you want to optimize energy, we should be able to identify equipment that are critical to the production. So for such motors, if they are not critical to the production, there is no need to even run them in the first place. Just let them be and run only the critical equipment. Thank you.
Good point. Thank you very much.
Please, one out, please, one out, please. I'm coming.
Yeah, speaking of fluctuations, I think there was a time I had to involve a technician on our pumping system. Now, I told the guy that anytime we have drop in voltage or electrical currents, that the pumping machine will not work. It won't pump until much later moments. Said, okay, increase the capacitor, change the capacitor from 30 UF to 45 UF. That was one, no result. Then that advice again to change to 50. Even at that, there was still no result. So I don't know, does changing of capacitor have anything to do, any relationship to do with voltage of the pump, the machine of pumping water?
Yeah.
Or what do you advise that we can do in that instance? So when there is no voltage.
So where was the capacitor that you changed? Where was that? The capacitor was a power factor correction? Where was the capacitor? Where was the capacitor?
Single phase, yes.
And he gave you the advice to insert the capacitor where? Where did you insert it?
The control box.
Where in the control box? Supply and...
Yeah, somewhere.
And it didn't work?
It didn't work.
Well, then clearly it's not a solution. And then the problem that you're trying to solve, what was the problem you're trying to solve?
The problem we're trying to solve is that when there is a drop in electrical supply,
When your voltage drops,
so once the voltage drops, the pumper machine would stop. It won't be able to pump. So the technician was like, look, it's because you have a small capacitor. Increase the capacitor to 45 UF. Once that is done, it will pump. But once there was no result, we had to increase to 50 AE, and there was still no result. So we had more or less had to go back, and each time they need to pump, end up using generator.
yeah, I have not heard the capacitor solution to single phase pump issues like that, so I can't tell you.
I think what I can tell you in that case is that the capacitor is not to improve the voltage. It's for starting the motor for driving. So even if you increase the capacitance to maybe 100 or 10, it will not produce your voltage.
What you have experienced, some party experienced that, which I later visit the place. The first thing I monitor the voltage. What current or what is the voltage rate of the motor? That's the first thing I consider. Then I look the input that is coming from national grid. okay, does it up to the rating standard of the motor? The next thing I just did is that I gave them ABR that can balance the voltage for the motor. And yes, automatically regulator. And then when you are shooting your ABR, you should consider the voltage of that environment. If the voltage is between 100, you should look for ABR that can work for 80 volts. Like it can give you your required output voltage for your equipment. That's what I finally do before they can enjoy.
But you can't do it in the power.
Yes.
Another question.
Thank you very much for the opportunity to speak. Permit my ignorance a bit for what I'm going to say. I'm not from engineering background, but I'm trying to keep up with the discussion so far. And the essence of my contribution now, or question, is born out of the last contribution with respect to the generator to power high duty or heavy duty machines and the rest. And my question is, how are we efficiently managing energy in that regard? Since we're talking about the energy efficiency. Question 2, if you now depend on a generator to power heavy duty equipment, are we not increasing carbon emission into the environment? Thank you, sir.
Let's tackle the first question. The first question was, is it more energy efficient to run a generator?
Please, one house, please.
Is it more, that's the question, right? Is it more energy efficient to run a generator? Okay. No argument about that. Your second question was the carbon emissions. You need to consider the efficiency of your generator and the fuel you're using, I assume it's diesel, versus the fuel efficiency of your central power utility, and I assume they're using gas or coal, and there are emissions there as well. And if you want to really compare emissions of your generator in terms of fuel consumed and the emissions factor for that versus what your national regulator publishes as their emission level, you can make that comparison and see which one where your emissions are highest. And that will give you an indication of where you are. It may be important for sustainability report to know that. So understanding emission factors of grid electricity and the fuel types we use are very important in doing and establishing the opportunities for or against using gensets or grid.
Like what you asked concerning the cost of the NGO managing the generator and all of that, this your equipment. After the first training that Mr. Alfred handled, he emphasized more on driving down the kilowatts hours. So when I went back, I looked at our equipment and actually discovered that there are a lot, because initially we were just running mainly on our 500 kVA generators. Okay? Meanwhile, there are some equipment that if we can get smaller air compressors, we may not even need to run the 500 kVA. We just run our 150 kVA. So I had to look at the equipment and identify all the equipment that 150 kVA can power with a certain size of compressor. Our compressor was 37 kilowatts that we run every day. So we had to go for a 7.5 kilowatt air compressor. So oftentimes, instead of running 500 kVA generator with 37 kilowatt air compressor and so many other big equipment, we run 150 kVA with 7.5 kilowatt air compressor and some other equipment. So we only run 500 kVA when it is necessary and we must run it. And when we did that, we drove down energy costs massively. So you can do the same thing. Identify the equipment that is smaller, that needs a smaller generator, smaller fuel consumption, and then you can only run them when they need be, and run the big gen only when you need it. You will save cost.
Okay. All right. Move on. One more. Okay.
Good everyone. I just want to ask this question, and might not necessarily truly related to what we're talking about, discussing in the previous lectures. Now, like in Nigeria presently, some factories are going off-grid. And when you go off-grid, you know you have to have a new balance. It has to go to conversion. And of course, you know when you do those conversions, BWM, pulse-wave modulation, you know, it operates at a higher frequency. So what I'm looking at now, you are going off-grid, you are using inverter, and it's being converted to PWM, and now it's being reconverted through the drives. What implication does it have on the lifespan of the drives, and what implication does it have on the motors?
Well, for starters, I'm going to see distorted waveforms, and that distortion itself could, of course, mirror a non-linear load and could result in further harmonics. But I must just say to you, in response to what you shared, that I'm finding those companies that are going off-grid are also converting to DC motors, to DC plants, so there's no need for inverters. So they are changing their operations so that they don't need any inverters. They're simply taking the DC that's generated by solar PV, for example, or wind power generators, and they're using that in the plant to power the plant and most of the machines. If, however, you're going off-grid and you're going to still operate AC, then that becomes a challenge. And you can, through distortion of waveforms, increase the harmonics and shorten the life of the plant. Yeah. Pleasure. Thank you.
So this section will appeal to you. This section will talk very high level about how to optimize the steam system. And the generic steam system and the way we look at steam systems, taking that systems approach, means that we include in our approach generation, distribution, end use, and recovery. We don't only look at the boiler. We look at everything until we have any condensate that's returned from the process coming back into the boiler house. So typically the machine, and we'll talk about the machine type, I'm not going to go through it on the diagram, but we have generation boiler here, we have feed water economizers, combustion air, feed water pumps, and we have combustion air preheaters, forced draft fans, induced draft fans, and in end use we'll have isolation valves, relief valves, we'll have pressure reducing valves as we drop the pressure from one header, from one high pressure to a lower pressure. And then end use we'll have a series of very interesting equipment, either heat exchangers, direct injection in cooking vessels, dyeing machines. We could have in refineries a whole range of end use equipment where we capture the condensate through steam traps, and through that we have a condensate return line where we either cascade or we feed or pump it back to the boiler house. It comes back into the deaerator and it's fed back into the boiler again. We try and capture as much of that condensate as possible, because condensate is one of the purest forms of energy. You have just spent a lot of money on chemicals, you've spent a lot of money on fuel to heat your water to steam, so you want to capture that condensate. It's a really great asset and you don't want to lose that. So that's the generic steam system, and the components within that steam system range very broadly. But in generation, it typically is water treatment plant, deaerator, feed water pumps, fuel storage, fuel water storage, handling equipment, and the boiler. In distribution, we spoke about steam piping, PRVs, the relief valves. End use could be anything you need to use the steam for. And in recovery, we look at steam traps, condensate recovery, and condensate pumps. And there are essentially two main categories of steam boiler designs. One of them is the fire tube boiler. As the name implies, the fire or the hot gases are in the tubes. So what would come into your combustion chamber over here would be air and fuel. And air and fuel will combust in that zone. And what it does, it heats up the water. When the fire tube boiler, the water is on the shell. And it heats up that water, and the gases then travel. These are called turnaround sections. So that's a turnaround section there, and that will be a turnaround section there, and then out through the stack. But we have passes. We call them 2, 3, or 4 pass boilers. That's how many times we turn around that hot gases to extract the value in heating that water to steam before we eject it. So these are the fire tubes. Water, I said, is on the shell of the boiler, and ultimately the steam, and sometimes we'll have, in this area, we'll have a superheated coil to superheat it. But mainly saturated steam would leave that boiler at the end of the day. The designs vary from what they call a wet back or a dry back. Some boilers will have another compartment of water in there to cool down and protect the integrity of the boiler structure. So that's a fire tube boiler. Typically 20 bar maximum, 20 tons per hour. I find a lot of those in industry, in agro-processing plants. They are generally in small plants. Many of them I find are 10 ton per hour. One inherent advantage, as I said, is that the radiant heat losses are very low because we have water on the shell. They are manufactured off-site, they transported and installed in your plant, and there are many different styles, as I said. This is when you take the covers of the boiler, or the flaps, the front end flaps off, you see these. These are the tubes. We normally service that, we brush it out, mechanically using brushes, or we can clean them out using chemicals. So that there is the heat exchanger that I spoke to you about. This boiler you could see, there's one pass in the furnace box, that's a second pass, there's a third pass. So that fire has gone down the combustion chamber, turned around, came back out here, and then turned around and went back in here again. So that's a 3-pass boiler, and that's how we signify that. Water tube boilers, they're the workhorses of industry. Water tube boilers, much larger. They range from atmospheric to 250 bar pressure, steam production from 2 tons per hour to 5,000 tons per hour. All power plants use water tube boilers. We can produce essentially superheated steam with them, but these boilers can be used to generate saturated steam as well. Superheated steam because we drive our steam turbine with superheated steam. You can construct these on-site mainly, but you can also get smaller versions of these that are constructed off-site. And we now have very compact units in the market, smaller water tube boilers that we haven't seen before. Here's some images of it. That's a large water tube boiler, that's the stack over there, boiler. Here we have a smaller one. This here is I think this was about a 2 tons per hour water tube boiler, a very small one. That's an intermediate size. We have auxiliaries in and around the boiler house. So what you see here is essentially the heat exchanger. It's a feed water economizer. It extracts the heat of the flue gas, so the hot gas going up the stack, and heats up combustion air or heats up boiler feed water going back into the boiler. Here we've got some flue gas treatment. It could be electrostatic precipitator or a scrubber. Here we have a forced draft fan. So we've got forced and induced draft fans. We want to maintain a negative pressure balance in the combustion box. We do that by linking the forced and induced draft fans. We have combustion air preheaters where we heat the air going into the combustion box, so that means we use less fuel to convert the water to steam. We have excess air control sensors, soot blowers, and we could use steam as a soot blower to clean it out, or we could use compressed air. In Cape Town, where we have lots of wine, grapes, and wine production, we have a seasonal production. So in the 6 months of harvesting grapes and producing wine, the boilers work very hard. And the 6 months after that, when they're starting to clean the vineyards and weed them, they open the boilers and they blow the soot on it. Because in Cape Town, South Africa, coal is a very popular fuel because we have rich deposits of coal. So coal is a popular boiler fuel in industry. You can get pollution control equipment as well. Then something I seldom see in steam systems in the world are deaerators. Which of you that have a steam system have a deaerator? Deaerators remove dissolved oxygen from makeup and boiler feed water. Why do you think? Why do we need to remove dissolved oxygen from boiler feed water? Oxygen at high temperatures becomes very, very corrosive. You allow that oxygen to go into the boiler with the feed water, and you elevate that to temperatures of 150, 180, 200, 250, you're going to cause serious problems inside the boiler. One way I normally detect that is I would take a blowdown sample, and the blowdown sample is colored as a rust color, a dark red color, or a black color. It tells me that there was a problem in terms of rust inside the boiler. How did it happen? They didn't remove the dissolved oxygen. So what we do, we use deaerators. The deaerators are lightly pressurized, 0.3 to maybe 0.1 or even something like 1.5 bars. So what happens, we have a spray type or we've got a tray type. So the makeup water comes in at the top of the deaerator, and there are a lot of nozzles where it will spray it from tray to tray, where there's a steam inlet at the bottom that comes up, and as the steam rises up, it physically strips the oxygen from that water and it strips the oxygen, the dissolved oxygen from that feed water and vents that. So that is oxygen-rich steam being vented there. As a result of that, the feed water that leaves and goes into the boiler has much lower levels of dissolved oxygen. The target in terms of dissolved oxygen is something like 7 to 40 parts per billion. That is the target. We want to remove as much oxygen as we can to a level of 7 to 40 parts per billion. Now, what is the dissolved oxygen in water, oil feed water? In groundwater, if you're using a borehole, your dissolved oxygen can be at a level of 2 to 3 parts per million. If you're using water from the municipality where it's been filtered and treated, you'll find that the dissolved oxygen could be anywhere between 5 to 9 parts per million. I'm saying we must reduce that to 7 to 40 parts per million. And that's why deaerators are important. If you don't have a deaerator, you are shortening the life of your boiler because you're rusting. But there's another solution. There's a chemical solution. So what we do is we will dose this water with an oxygen scavenger. And the oxygen scavenger removes oxygen from that boiler feed water to reduce it to 7 to 40 parts per billion before it enters the boiler. But that water chemistry is very important. If you're not a water chemist, you find a good water chemist and form a relationship with them. They're an important partner in terms of your boiler system. So you need to ensure that you're achieving the levels of dissolved oxygen that won't cause problems in your boiler. All I see in a lot of plants, they have an open well. And they're heating up, the condensate comes in there, the steam that goes in there, the makeup water that goes in there, they're heating it, and I see some steam coming off that. Not good enough. You need to be pressurized. Many plants I work at, they have a vessel, but the vessel is not pressurized. And what the kind of things we do to create that pressurized vessel, we insert a gate valve at the top of the deaerator. And I take my drill and I drill a hole in that gate valve. 6 millimeter valve. That's good enough. And with that, I will be venting my oxygen-rich steam and stripping it from the water coming through the deaerator. So that's an important, something that we need to be very cognizant of. Pumps, we have many. We have boiler feed water pumps, like we have over here. We have condensate pumps, makeup water pumps, other auxiliary pumps. Water treatment is critical. Do not forsake this. Do not neglect this. The quality of water will greatly enhance and improve the quality of the steam and the longevity of your boiler. So, several options. We have softening, dealkalization, demineralization. Reverse osmosis is becoming very popular now in many steam systems. Condensate polishing. So your condensate comes back from the process and it's a bit dirty or it's stained. You clean that. You put it through filters. You use an ion exchange to remove some of those impurities. And you clean your condensate and you send it back into your deaerator to go back into your boiler. So you have chemical treatments for that as well. There's the reverse osmosis plant over there. And then steam piping. We need to be aware of the importance of the integrity of steam pipes. How we insulate them, the pipe racks that carry them there, where we have drain legs to remove any condensate from those pipes. We need to insulate some of them, especially if our condensate temperature we're returning is at a very high level. We want to capture as much of the thermodynamic value of condensate when returning it to the boiler. Pressure reducing stations. When you generate steam at 8 bar, or 7 bar, or 10 bar, but you only need it at 5 bar, you drop that pressure to a pressure reducing valve. It's a complete waste of all the energy. Because all that happens, the entropy at the inlet and outlet to your PRV is the same. There's a slight temperature drop, and all you're doing, you're giving up pressure to meet the requirements of the machine. You're not putting that steam to work like through a turbine, steam turbine. But this is typically how you can identify a pressure reducing station. You will always see that you have this kind of valve, and that's the PRV, the pressure reducing valve, that operates feedback loop. You can see there's a feedback loop when you need to work on it, repair it. We also need the bypass for emergency and repair conditions. So PRVs also normally have a pressure gauge on the inlet and outlet. So it will show you how much it's dropping your pressure by. The amount of PRVs in a plant, you can either do PRVs from header to header, or you could do PRVs from the main header to each machine. I had a plant in Sri Lanka where they had 40 presses, 40 machine presses, and they had a PRV at each one of those presses. It's a bit excessive. If I had the choice to redesign it, I would have put in a secondary pressure header and do one PRV and run all my presses on the secondary pressure header that way. Steam turbines. Turbines are devices which convert thermal energy into sharp power. They can generate electrical power through a generator. They can drive mechanical equipment. Steam turbines, I've seen them operate their force-draft fans, the boiler feed water pumps, with steam turbines very effectively. Different types of turbines. We have a back pressure turbine which discharges onto a pressure header, and hence the name back pressure. So you get high pressure to medium pressure, steam back pressure turbine, or medium pressure to low pressure, steam back pressure turbine. You've got extraction turbines, where you could take intermediate extraction onto a range of headers, and extraction turbines are used to balance many headers. You have condensing turbines. Condensing turbines generate electricity, and what are the main benefits and reasons of that. Or you could have a combination of all these turbines in one steam system working very well side by side. Heat exchangers. Heat exchangers is end-use equipment, and heat exchangers do a lot of work in end-use applications. We have a few design options in heat exchangers, from a shell and tube, that one, to a plate and frame, which is this one, tubing tube, spiral, and others. What's important about heat exchangers and understanding when they are effective is what we call the approach temperature to a heat exchanger. So if I could draw this for you. say that there's steam coming into your heat exchanger. That's saturated vapor. And let us say that there's condensate leaving. So that's saturated condensate. And let us say that we have water coming in at this temperature over here and leaves at an elevated temperature. We've warmed the water because we have used and absorbed the energy from the steam. If I call that T2, and that T1, and this T3, and this T4, then approach temperature is T2 minus T4. And we want to achieve approach temperatures of 6 to 10 degrees Celsius. 10 degrees Celsius tells us that the heat exchanger is functioning effectively, that we're getting a good transfer of energy from the steam in heating the process or the fluid that passes through the heat exchanger. Thank you. Heat exchangers can be another course on its own. We can spend a day talking about them, but it's important to know of them, what they do, and why they're important. So in heat exchangers, when I work in plants that have a lot of heat exchange equipment, I expect to see a high level of condensate return. Why? Because I'm not using the steam to heat the product. I'm using the steam to almost induct heat into the process. So I expect in heat exchangers to have high levels of condensate return. It varies from process to process. In agri-processing plants making food and biscuits and jams, I expect high levels of condensate return. In rubber tire companies, where there's a lot of impurities with a little rubber nipple when they inject the rubber into the mold, a lot of that in the condensate is impure, I can't take it. I'll try and filter that out. But the condensate return in rubber tire companies are very low. They're of the magnitude of 30 or 40%. So condensate polishing becomes quite an important function. We've got quite a few other uses. We've got the feed heater, the cooker, the dryer, the hot water heater, and many others. I've seen retorts where they have cans of baked beans put into a large sealed container, pump steam into it, pipe steam into it, heat and cook the baked beans, remove the steam, capture the condensate, and remove the baked beans. Steam traps. Steam traps are important for removing non-condensable gases and condensate from steam lines and starting up a boiler, and from removing condensate during normal operation of the boiler. There are several different types or categories of steam traps. We have what we call thermostatic steam traps. And thermostatic steam traps respond to changes in temperature. Mechanical steam traps respond to changes in density. Thermodynamic steam traps respond to changes in velocity. And orifice steam traps respond to changes in pressure. So what those steam traps do, when there's a change in temperature, pressure, velocity, it simply opens the trap. It discharges condensate, sometimes with a little bit of steam, and closes whenever it is restored. Just to show you what we have here, so you can identify them. That there is a thermodynamic steam trap. This is an inverted bucket. This is a ball and float, a thermostatic. Here's just an example of a trap failed open. When a trap fails open, you can see it and you can respond to it. When a trap fails closed, it's a very different kettle of fish. When a trap is failed closed, what it does, it backs up condensate in the steam line. So the plant now is not seeing that approach temperature from the heat exchangers. And the plant manager may shout and say, I need more steam, I need more steam. When really what is happening is the steam trap is failed closed, and now you get the buildup of condensate into the steam line. As a result of the condensate in the steam line, you start getting water hammer. And you get the big tubs of your steam line that could, over time, impair the integrity of your steam lines and cause damage to it. So steam traps that are failed close are very, very seldom noted until it's too late and they've caused a lot of damage. We have condensate recovery systems. This is probably one of the most neglected opportunities in a lot of plants. What do most plants do when they've used all the thermodynamic value of steam? They discharge condensate to drain. They don't use it anymore. And that's valuable. So we need to find ways to capture it and return it and use it. We can change, it'll come back and we'll change the settings again. That's an inexpensive way, but it's not a really efficient way of doing it. The way to do it is through automatic tune. Much air in your combustion box because you end up wasting energy to heat up nitrogen. So you need to limit the amount of air, and that's why this sensor is so very important, this flue gas sensor over there. The last thing I want to leave you with, in terms of calculations, is how to calculate the steam leak. Now, if you consider that steam leaks abound, and invariably steam leaks should be located in areas very far from where you are. So if you're standing on the floor, there may be a steam leak on the header over there. You may be lucky. There may be a steam leak right here, which is quite dangerous, by the way, if that's known. But if you can measure the orifice size, or you estimate the size of that hole, and Napier's choke flow equation uses something that's called the coefficient of discharge. And the coefficient of discharge if that's the pipe, and that's the orifice. We'll look not only at the shape of that orifice, is it round, is it long like that, but we'll look at the edges, is it serrated, or is it smooth? And it looks at how steam would escape typically from through an orifice from the steam header. And they develop, as a result of that, they develop this coefficient of discharge. And for steam, we generally use a coefficient of 0.69. So we apply that in calculating our steam leak loss. And the formula that we apply is the mass flow rate of steam at that steam leak is equal to the coefficient of discharge, which is 0.695, multiplied by the area of the orifice, how big is that hole, multiplied by the pressure of the steam in that line, or that header. So, applying that, and as an example, we had approximately a 4 millimeter diameter hole in a 2-bar gauge header, calculate the steam leak. So what we did, that was the formula, so we used 0.69. The area of the orifice was 4 millimeters. Pi r squared gives us 12.56, multiplied by 3. Why 3 when it's 2-bar gauge header? We use bar absolute. So that's 3 bar absolute. It gives us a steam loss of 26 kilograms per hour through that 4 millimeter orifice, a 4 millimeter hole. You can now apply that for all your steam leaks in the plant, multiply that by your marginal cost of steam that you calculate to measure, and you can determine what the cost of those steam leaks are. And when you present it to management as a good project, you can actually present the economic impact of repairing the steam leaks. Following are some common best practices in steam systems. I'm going to touch on a few on each page, and I'm going to leave this with you in the slide as a reference. Believe me, they are valuable. And if you are looking to optimize the steam system, you don't have to go and reinvent the wheel. Here, these are lists in each of the 4 components of the steam system: generation, distribution, and use and recovery, that can indicate where you can save money and energy. So you want to minimize your excess air, and you want to do that with automatic room control. You want to install heat recovery equipment. I want to feed water economizer to warm up my boiler feed water. I want to capture the air from the flue gas to heat up my combustion, to preheat my combustion air. Clean your boiler heat transfer surfaces. Clean those pipes. Clean those tubes regularly when you take the boiler down. Recover the energy from blowdown. As we said, the heat exchanger would be an ideal way to do that. Watch your boiler refractory. How do you do that? Often I would take my thermal imaging camera and I would go across my boiler shaft. I would take a photo every square meter. I would save that on a small file, like a TIFF file. I would put that away, store that as my baseline. I'd come back 3 months later, 6 months later, or a year later, and I would do the same. I would then compare my baseline photos with my current photos. And it will reveal to me where I'm getting some early signs of refractory losses. That gives me an indication of where I need to start preparing insulation. So that's an opportunity. Fuel switching is a very big step change, but it's also very difficult, and it doesn't come along every day. You want to switch from diesel to natural gas, you want to switch from coal to biomass, you want to switch from HFO to LFO, you can do the numbers. You may have to modify your temperatures, your burning temperatures. You're going to heat the diesel before you can feed it into your combustion box. So or through your burners. There's a lot of things you need to consider. It's not only that simple. In distribution, steam leaks. Minimize vented steam. AB InBev is one of the world's largest brewers. They have a philosophy at all the breweries. They don't want to see vented steam. When they come on site and they see any vented steam, they want to know why. What is the cause of it? Why are you stopped? So vented steam is a big loss, and they recognize that. You want to ensure that your insulation is good. And I've seen some incredible insulation at steam plants. The AB InBev brewery I worked at Newlands in Cape Town has a jacket, besides all the pipes being insulated, has jacketed insulation for every flange, every valve, every vessel. So they have minimized the radiant heat losses. You want to isolate steam from unused lines. If you can, take those lines down. You don't want to have isolated lines no longer requiring steam. Reduce the pressure drop. You don't want heavy pressure drops in headers, and capture your condensate. Get them out of your areas. From an end-use perspective, you want to improve the efficiency of the process. What are you doing? Sometimes by simply installing a preheater or a pre-cooker, we can reduce steam in the final cooking process. So consider that when you're looking at how you're using steam. Shifting steam demand to waste heat sources. Can I use any of my waste heat instead of using steam? Upgrade low pressure or waste steam to supply process demands. There's something called a thermal compressor, where you take medium pressure and low pressure and you reduce elevated steam pressure. They are commonly used in dairies, in milk dairies, UHT milk. The thermal compressors give rise to steam pressures that you otherwise would have used the pressure reducing valve on. Recovery, implement an effective steam trap management and maintenance system. There's a rule of thumb that says the steam trap is going to fail every 10 years of its life. So that means, expressed in another way, that 10% of your steam traps are going to fail every year. There's also a belief that you should look at and examine your steam traps once every 6 months. But the critical steam traps in your plant, you need to look at once a month. Because if a critical steam trap fails, you get a failure of a critical process, and maybe your plant comes down with it. So steam trap management is important. You want to capture as much condensate at the highest available thermodynamic value. You want to flash high pressure condensate to make low pressure steam. So those are some of the opportunities to optimize the steam system. I want to play. Are there any questions before I play? Any questions about steam systems? If you find any of that valuable, is there anything you can take from that and go and apply in your plants? I will give you, and I'll put it up on the flip chart, so when you're having lunch or after lunch, you can get it from the flip chart. I'm going to give you the addresses for steam system scoping tool and the measure tool. It's a really great tool.
the fully insulated steam line.
Yes.
How do you do that?
You can't see the steam. The steam leak is under the insulation, no way you can see it. You have to get the scaffolding up, take the insulation away, and then repair that.
But we are talking about energy conservation. Yeah. So if the lines are not insulated, there will be heat losses into the environment.
Yes.
And one of the measures to optimally use steam and energy for thermal energy from steam is by insulating it.
Yes.
You find out that a steam leak is very common on the line.
Yes.
And they will need to estimate it.
Yes.
So how do you do that?
You have areas of the steam piping that will not necessarily be insulated, like maybe the steam pipe going to the machine itself. It is a very short length of pipe, maybe a small diameter pipe, where you could have a steam leak. You could have areas on your steam headers where your insulation extends to maybe 10 millimeters to the flange. You could have a steam leak at that piece of air pipe. You could have a steam leak at a CIP. So it is possible to have steam leaks in uninsulated areas, but you make a very good point. If our insulation was thorough, we shouldn't have seen the steam leaks. But as it happens, plants have steam leaks. You find them in sometimes the supply to the end use. You find them in headers that are not insulated. And in many cases, the steam leak will happen quite across the plant. And I've seen steam leak at Galvez.
Why I have this question is that I've worked in the canteen, hard work industry. And whenever you want to check our pipings, you need to strip off all the insulators to check the pipings. And at times, you have to shut down the factory probably for 2 weeks for them to do all the pipings, reticulation, and doing everything. And as we raise it now, that's why I give it to concern that it's not easy to check out because right from the boiler room, all are insulated, only to the point of usage. You have to step it up and then take it to the equipment. So, and whenever you want to now do that, in fact, it's a real maintenance project that we have to shut down the factory probably for 2 weeks, no more than that.
Why do you strip the insulation from the headers? Why do you take the insulation off the pipes?
Like probably maybe they notice that there are some problems online, and they want to do total maintenance. Because by the end of the year we do maintenance, we check the boiler, we discard the boiler, we open the boiler, all the pipings, the treat and everything. So
it's a very expensive exercise, removing all your insulation. Is it really worthwhile doing that? I must tell you, when you talk of perfect insulation, you're talking the perfect steam plant. I'm going to see steam plants in Lagos in the next week, and I can tell you that I will find steam leaks and steam headers that are not insulated. Because that is what happens in real life. Not every inch of steam piping is insulated.
Yes, but those ones that are not insulated are minimized. Probably towards the point where you want to take it into the equipment. You step it down, then you have all the valves, the condensate trap, all those things. Those areas are the major areas that you do normally.
Yeah, you could also have a defective steam trap, and you could have, as a result of that, steam escaping from the steam trap.
I think in regard to the question he asked, I'm looking at it that you don't need to strip everything, because one thing is obvious. Whenever you have a leakage, steam leakage over time, water will be dropping. So you will see it. You will know that section. If you are going to strip everywhere, you just strip only that section. Not that you strip everything and
But at times, you know that water, the point at which it's leaking will not probably be the point at which it's
yes, that's why I mentioned section.
Because you travel through the insulator and then the point where you find to stay out.
Yes.
That is where you now be filling the water. And when they are trying to now trace it, you understand, we are trying to trace it because it might be leaking here and water might be dropping here.
Yeah. That's why I mentioned section. Depending on what position. The position of the pipe
and determine where the water will flow.
But you know, I would take my steam installation and I would feel my installation if it's wet. And I can trace the point of the leak by just feeling where it's wet. And as he suggested, only removing what you need to do, not the whole lot. Because that's...
Hello, sir. Sorry, in our system, we don't use steam boilers.
Yeah.
We don't have steam as, okay, we have steam system anyway, for different application, we don't require installation. I mean, our vaporizer, yeah. So, but then, if maybe removing the soil insulation, like you said, is costly,
yeah.
I'm just thinking,
yeah.
Is there no system in place like maybe an X-ray or a photo something that can reveal the internal condition of the site, so you don't need to strip all the insulation? So that when you shoot a camera or something, you can see whatever is happening in the inside from the camera and know exactly where to attack.
How do you think they pick up leaks in water pipes in walls? They have cameras.
Good. So instead of going stripping all the insulation, why not just do that and go straight to the point?
Well,
that's to say that not on the same questions, but then I'm still thinking that the teaching was going on. In our own system, we don't use a complex system like you are teaching, but we have a system, we have a loose chiller. Okay? Now the chiller is more or less a cooling system. That is what we use.
Yeah.
So I don't know if this training also incorporates anything like that in its chiller system.
Oh yes, we have the same kind of training for chillers. I had to decide what to leave out and what to leave in. And in this course, the centrifugal devices were critical. Considering the ambient temperature in Nigeria, chillers and the refrigeration were top of mind. Process heating was another one that I considered as well. But the more I added in, the lighter the depth of the coverage would be. But you're right, I think chillers and refrigeration become, especially chilled water systems, cold rooms, becomes an excellent opportunity for Nigeria considering the temperature.
Yes, so maybe your next course,
yes,
you can incorporate it.
Absolutely.
And maybe invite us again so we can also benefit.
Thank you. Thanks.
Let me answer it. In this fire tube boiler, you show us here.
Yes.
This one type of
yes.
are using.
Yes.
Like open. But I want to ask you a question. What can really cause chimney collapse? When chimney collapse, you are using the listen. What is it? You are using. We're using the no, it's not it's collapse. Chimney collapse.
What collapse?
Yeah, the chimney of the boiler collapse.
The chimney collapse.
Yeah.
Ah, it's not an uncommon problem. What is your fuel that you use? What is fuel?
We use gas, LPG.
That's quite unusual for LPG to see.
Eco-flame boiler.
What did you use before LPG? Were you always using LPG?
Yes, we use LPG.
I tell you what normally would be the cause of that. We call it acid dew point. Okay. Solid fuels, HFO, LFO, fuel oils, all have high sulfur content. So when you have flue gases go up your stack and they condensate in your stack, they produce sulfuric acid. Okay. And the sulfuric acid starts to eat away at your stack. And I was at the brewery where the stack was about to fall. And there were people living right next to the brewery. It could have fallen on some houses and killed some people. But the plant maintenance man spotted it. And then they took the chimney off. But the neat cut caused by sulfuric acid was the cause of it. You're using LPG, we shouldn't be seeing that in LPG gas. So I'm quite interested to find out how that happened, because that's unusual.
Hello, sir. Anyways, somehow, when we carried out the breakdown maintenance, so we carried out the repair of the chimney, curing oven and all of that. We had to tear open the chamber that accommodated that tube we showed you in the picture. That's exactly the one in our system. So we discovered that there were a lot of carbons over time that had accumulated inside the heat exchanger
Therefore, it was no longer possible for the heat to escape. You know, it's supposed to go through the system, but because of the excess carbon, the system was blocked. So there was no way for heat. Yeah, the heat exchanger, the tubes, those tubes.
Yeah.
So there was no way for the heat to escape. It has to find any means, and that was the cause of the explosion or rupture that collapsed the chimney. By the time we serviced that chamber, in fact, we scooped out a lot of carbons with bagger. We shorted out a lot of carbons.
So when did this happen? How long ago was that?
Man, this was like 2 years ago, right? So since then, we decided that once every year, we tear open that chamber, carry out thorough maintenance to prevent subsequent occurrence.
That's how we learn, eh?
What can we do again, apart from that one? Is there any alternative solution? Apart from what you said, is there any alternative solution that we can do again instead of open it? Is there anything you can use?
You get a build-up of carbon from using LPG gases. Okay, then we need to share some information after this training. I want to find out more about how that happens, because I shouldn't have built up of carbon using LPG gases.
Yes, but from observation, one other thing personally I tried to control that situation in the plants was that whenever we are firing that burner, I tend to ensure that we achieve blue flame instead of yellow flame. Now, yes, some persons do not know what I was trying to achieve because they want to see yellow flame to show that it's really burning well, but no. Personally, I try to achieve blue flame to ensure cleaner energy so that formation of carbon will be reduced to the barest minimum. So if you take a very long time for carbon to build up in that system, thereby reducing the risk of such a explosion. But if you continue using high flame, yellow flame, the possibility of carbon building up easily will be there.
I agree.
We also service the burners. At interval, we bring down the burner, service it, check it outside, set the flame before we fix back again.
But you see, the method of your install, how you mix your energy with the air for combustion.
It's a closed system and a neutral system. So if you don't get the right,
it's a closed system. For total combustion to work, there will be proper mixture of air and emission. If your air and the gas are not this problem, so
yeah, that is where the settings comes in.
Okay, so to come back to your point, the way you can prevent this is to take very irregular readings of your excess air, excess oxygen in your stack. And when you start to see that excess oxygen level rise, it's an indication that you have too much air in your combustion. So you need to cut back on it. Okay, so that's one way to do it. Can we start the video? Question?
One more question.
So my question is in the area of the softwares. The softwares that show us. The softwares.
Oh, the software, yes.
Are they user friendly?
Yes. The good thing about Measure, it has a few manuals that you download from the system, few guidance on how to use the tool. So they've thought about that a lot. They provided a lot of additional support by way of download. So you can go and download some.
Second question. So it's quite a lot of information to process. If you are going through this manual, if you encounter any challenge, the command will
You have two choices. You can contact Oak Ridge National Laboratory directly, or you send me an email. If I'm not busy training somewhere in the world, or if I'm at home, I'll get you an instant reply. But that's the way of doing it. Oak Ridge National Laboratory as an office where you send your email query and they respond. But you can also send me and I'll respond. Okay, thank you.
The last question, please.
So we can have the video now.
Yeah, thank you very much for your questions. Where is the best location to install the central to avoid
Spirax Sarco is an international supplier of steam system equipment, boilers. They don't really do boilers, they do steam system equipment. They do training a lot. Spirax Sarco has a rule that you should have a steam trap every 50 meters of pipeline. So you must add up all your steam pipelines, divided by 50, and that should be the number of steam traps. I don't know if I subscribe to that. To me, I need to see what the quality of my steam is, what the level of condensate I have, and position my steam traps. Normally, you would position a steam trap after a heat exchanger. At the exit, at the outlet of the heat exchanger. Because you've got steam coming in, you've got condensate going out. That's where you want the steam trap. So at every end user, where you are using the value, the thermodynamic value of steam, and you're discharging the rest, that's where you want the steam trap.
What I'm asking this question is why steam traps are already failing. So
They are not failing.
They are failing.
They're failing.
So I was thinking installing it closer to the end user would be better after the extension.
Yeah. They're failing. For other reasons too. We could be failing because the steam trap is undersized. Undersized is too small. No, the steam trap itself, you get different sizes. You have to put the right. So you need to do a root cause analysis. Why are we having the failure of the steam trap? When the steam trap fails, you just got another one. You must find out why it failed. It may be that more than simply the location of the steam trap is causing it. Okay? You're having the same problem. Okay.
My second question is calculating the efficiency. Considering that we are having the heat from the recovery system, maybe from the electrical source to the boiler. Should we still need to consider the stack loss during the calculation?
So when you say you're getting heat from where?
Maybe from the generator is also the boiler. I'm not using boiler in this.
Oh, you don't have a boiler?
Yes, I'm not using boiler in this situation. I'm using the heat recovery system for my generator exhaust line to heat up the tubes of the boiler to generate my steam. Should I still need to consider the stack loss during the boiler efficiency calculation? Yes, yes. We heat up the boiler. Yes.
For that instance, the efficiency you are looking at is not the efficiency of the boiler, because it's the heat recovery process. You are looking at the efficiency of the recovery process.
So you don't need to take it. Okay, can we use?
The United Nations Industrial Development Organization, the Swiss State Secretariat for Economic Affairs, and the UK Department for International Development. The project is a collective effort with a single vision: to reduce carbon emissions by making South African industry more energy efficient and therefore globally competitive. The UAE project is a pioneering idea with a clear agenda of best positioning South Africa for a sustainable future. Hosted by the National Clean Production Centre South Africa, the IE project is a front-footed, fresh and innovative idea. It's about making South African industry sustainable, starting with its energy-intensive sectors.
The idea is exactly that. It's to as a start to focus on energy-intensive industries because we believe that there is where the greatest opportunities lie for energy efficiency and reduced energy usage. But certainly we are going into the SME market and assisting the SME sector, industry sector, in improving the energy performance.
institution for South African industry, the Department of Trade and Industry, along with the Department of Energy, are important stakeholders in the IEE project.
For DTI, energy efficiency is quite important because the South African industry is highly energy intensive. So going forward, the DTI sees the national cleaner production as really the key mechanism to ensure that we change the paradigm, we move over to become more and more energy efficient.
What makes this project so unique is that South Africa is the first country globally to roll out this kind of UNIDO implemented energy program. With energy efficiency being a global issue, it was the South African government's willingness to tackle the energy crisis head-on that led to a task force of international energy specialists collaborating with local industry to initiate the IEE project in March 2010.
Energy efficiency has to be evolutionary rather than revolutionary. It has to come from the ground up, from industry, through management, through the commitment of management to changing corporate culture. But obviously there has to be strong government support, commitment to actually, I wouldn't say forcing the industry to change, but encouraging them to change and giving them the tools to overcome the barriers which they face.
In tackling the South African energy crisis, industry soon realized the importance of linking arms and learning from international experience as the best way to tackle the local energy challenge.
In a time where we are now, where energy is now an international concern, thinking about it, I think half of the world currently is suffering from shortage of energy capacity. So it is important that when you deal with issues that has got international impact, you allow yourself to learn from other countries and how they dealt with those problems at their level in their countries.
With international and local funding, the IEE project aims to assist energy-intensive industries and SMMEs in finding solutions to making them more sustainable. The project's approach to industry participation is simple. Companies are recruited to showcase energy-saving impacts as a result of the recommendations by the IEE project. Over a 4-year period, these findings will hopefully help shift the behavior of South Africa's key energy-consuming industries, while also benchmarking the effectiveness of the initiative.
The idea is that after 4 years, we'll be able to measure the amount of energy that was actually saved because of this project. And because this project has a clear, measurable target for any participant, we feel that going forward, all the companies that participate and those that don't participate will actually want to get involved. It's one of those projects in the environment sector where measuring it's very straightforward.
In the heart of the Western Cape's West Coast region is Saldanha Bay, home to ArcelorMittal's Saldanha Works plant. This steel manufacturer is the single largest user of energy in the Western Cape, with a maximum demand of 160 megawatts. The ever-increasing price of energy now has a real and direct impact on the bottom line earnings of this export-driven operation.
Energy efficiency is extremely important for this site. We focused on the export market, which means that our competition is not seeing the electricity price increases that we're currently seeing. And in order to make sure that we can maintain our competitive position in the export market, we need to make an impact immediately in terms of energy efficiency.
Tasked with overseeing both the energy needs and operational demands of the plant, Renette van Zyl is passionate about turning this steel plant into an energy-efficient site whose product is also globally competitive. Through the IEE project, Renette has been able to turn her implementation of energy management into a systematic approach with her company's backing. The benefits of the program have given her the confidence to implement systems that will work for her business well into the long term.
It's a very structured and systematic approach, and I think we started working on the energy strategy before we got involved with the program, but where it really assisted was looking at organizational and also behavioral aspects within the work environment. We find that we engineers, we tend to focus on the technical aspects, but if you want to make sure that you have sustainability in whatever you are implementing, that is where this energy management system is excellent, because it's looking at the other aspects that will make sure that the effort and the impact that has been made will be sustained.
With primary exports to Africa and international markets, the ArcelorMittal Saldanha Works plant is serious about long-term sustainability. The plant uses vast quantities of coal and electricity every day in order to meet its energy demands. However, with increasing prices in energy, its profitability is at risk. The only answer is to critically address the energy efficiency issue at a strategic level through energy management.
From a survival point of view, we have to focus very aggressively on energy to make a sustainable difference for this operation. And I think from a second perspective, it's the right thing to do. We have to focus on energy because we have to make sure that this plant is there for the future.
Involvement in the IE project has given ArcelorMittal the tools to critically assess its energy needs and find a framework to make these more sustainable. The direct impact of the IE project are the triple bottom line savings that translate into tangible results.
Looking at electricity specifically, we've managed year to date to, on that average demand of 160 megawatt, to save 6.7 megawatt, which is, it's a full 5% saving, but in terms of the impact on your monthly electricity bill, it is significant.
A sector that knows all too well about the recent crippling effects of globalization is the automotive industry. But equally so, it's a sector that's making positive strides towards efficient, sustainable manufacturing. Welcome to the world of Toyota South Africa. Toyota South Africa celebrates its 50th birthday this year, the legacy of an iconic South African brand. However, the history of the brand is underpinned by the story of its people. At Toyota, the energy efficiency strategy is focused right across the value chain, from materials and most importantly, through to its people.
So the energy efficient behavior part was probably the behavioral of the people. Getting people to switch things off when it wasn't being used. We developed slowly quite early in Toyota that no work, no what was our slogan at the users. If you're not working, switch it off. Especially over weekends, between shifts, tea time, lunchtime. That was probably our biggest change, was actually changing the mindset of the people and carry that learning home with them.
The Toyota plant in Prospecton, Durban, produces over 640 cars per day, each car being assembled on-site, polished and ready for retail. With over 6,900 staff working on site, this plant is one of the 4 largest energy consumers in the Prospecton industrial area. Through careful assessment of its supply chain, Toyota South Africa, together with the IE project, has identified key energy savings, particularly when it comes to the amount of electricity required to produce a single vehicle. From 2009 to 2011, the electricity required to produce a car has reduced by 33%, a welcome reduction in CO2 gases.
One of our first energy projects we identified in this particular area was there was a lot of lighting in this particular zone. So we measured the light intensity here. Found there was way over the requirement of what they actually needed. So a lot of waste for the energy put in too many lights. So our project here was to actually remove 3 second lights as it was until we got the right light intensity required here for the process.
Already on a journey towards cleaner production, being part of the IE project has given Toyota South Africa that added boost, catapulting its energy rankings both locally and internationally.
We've made significant improvements in the last 2 years already. I think we're one of the worst performing Toyota plants from an energy efficiency point of view. I think we're now ranked in the top 5 worldwide. So that's what we've done in a short space of time. We certainly want to continue that. We're not there yet. Continuous improvement.
The direct benefit of the Energy Management Program at Toyota is best articulated in the words of its staff.
You don't need to spend a lot of money to get people to turn lights off. The simple reality is that there are opportunities all around us. And at first, if you don't see them, keep going and you'll see them absolutely everywhere.
The beauty of the IE project is that it provides a framework, a tangible strategy, backed by the Energy Management Standard ISO 50001. It's this technical measurement of energy savings and systems analysis that make the project an important initiative. This project focuses on skills training by recruiting international experts, guest lecturers, and industry leaders to collaborate with South African industry. To date, over 900 local industry specialists have been trained in industrial energy management system implementation and energy systems optimization. In a recent training workshop, IE project participants learned first-hand strategies on how to best implement fan system optimization techniques in their respective plants. Fans constitute a large percentage of energy consumption within industrial sites. These lectures provided an opportunity to share and learn from those with great wisdom and advice.
What we'd really like to encourage South African industry to do is to take a close look at what are the needs of the process and then allow someone to come in and match the capabilities of the fan to the needs of the process.
I can't get fans out of my mind. I should have retired, well I did retire in 1999 and the following day I was taken on as a consultant. I enjoy fans. It's a passion in my life. I wouldn't know what to do without fans.
As companies are recruited to be part of the IE project, they become part of a global dialogue, a collection of industry specialists finding clever ways to do things differently. The IE project aims to be absorbed into the structure of the National Cleaner Production Centre South Africa at the end of the 4-year period and is heralded as a legacy project for the country. The Industrial Energy Efficiency Improvement Project is a collaborative effort that puts South African industry at the front and centre of the energy efficiency global discussion, showcasing a nation's concerted effort to make a change for the benefit of future generations.
So, any questions? We come to the end of the training, we're going to enjoy lunch. But any questions about how it's about anything particular besides what's already asked? Okay. Then I'm going to say let's enjoy lunch. I think lunch is ready for us. Thank you very much for your time. And I hope you gain some benefit from this. Thank you. Thank you.
On behalf of the entire members of the Project Management Unit, we express our gratitude to you for all that you have shared with us. I don't know whether you observed, but I believe one of the benefits we've been able to draw from this is that we have the opportunity to tap into your wealth of experience. And most profound is the approach to teaching, which simplified a whole lot of concepts. And you are even willing to spend time to listen to concerns and also provide solutions to those challenges. So we are very, very grateful on behalf of the participants, and also promising on their behalf, because there will be time, I will have given mine to one of them to say that
that all that the learned will be implemented in our various factories, rest assured. And one thing, also speaking for them, that we'll do is possibly make available contact. Should they need further clarification, further advice, or suggestions from you, I hope you will be you will oblige to also find time, because I know you have a very busy schedule to respond to their emails. So once again, we say a big thank you to you. I also like to thank GEF-UNIDO Jeff for also providing this platform for us to also learn again, particularly with respect to IEE and RCP. I don't know, I know many of us really, maybe I'll say it this way, we've had the opportunity of being on this journey from as far back as 2021. Some joined the box along the line. But altogether, when I listen to the kind of questions we raise, when I listen to the kind of contribution we made, it gave us a level of assurance that the investment being made by Jeff and GEF-UNIDO to ensure that we are put on this course will not be wasted. So I'd like to also thank participants for being part of the process. You agree with me, you can organize a very beautiful workshop. If there's nobody here to receive it, then we won't be able to deliver the training. So thank you for your cooperation. Thank you for your support. But the great thing you need to do for us and for Nigeria as a whole is to ensure that you remain our ambassadors wherever you are when we talk about IEE RCP, starting from where you came from, your company, applying those things that we have learned. Few information, well, a number, one or two information, then we will call it a day. The first one is to say that as many that are yet to return their questionnaires, particularly for CPA, we want to plead with you or implore you to consult with management. You know, management consent and approval is strategic to what we are trying to do. Ensure that, then secondly, from feedback from our experts, some of those questionnaires are not properly, not fully completed. I think that's the right way to describe it. Either for sensitivity related to some information and all that. Where you require us to sign a non-disclosure agreement, we are willing to also do that, so that you provide those data, so that whatever report that will be generated, either through the assessment, from the assessment, will be of great value to your company, because those critical information in the questionnaire are vital, very vital to the analysis, the assessment, the expert about to do for us. The second information that I have to share with us, also a checklist. We've been advised by Michael to share that to everyone. It's not something that should be hoarded, because it's something that has to do with the environment, that has to do with all of us who are part of the environment. So even if you are not participating in the CPA and you've received the checklist, it's not just for us to take and return to us, it's for us also to go back to our various organizations and look at the checklist to ensure that we have all of these things in place. On that note, I think I would like to draw the curtain. MPC, is there anything you would like to pass across? Nothing. I would like to draw the curtain of this 2-day training workshop. Names. Okay, can we project it? Can you quickly project it? We usually do this so that we won't get your emails and names incorrectly, because if we don't have your correct email, should we need to share anything with you, we'll be sending to the wrong addresses. So that will come on screen. Obafemi, please help with the
Vice Chancellor.